Subscribe so you don't miss out on any of these videos. Imagine a time before galaxies, when the universe was young and dark. Somewhere in that void, the first black hole was born, a cosmic ghost lost to time. Now, astronomers are on a mission to find it, hoping to unlock the secrets of the early universe and the forces that shaped reality itself. The universe is filled with mysteries, but few are as profound and elusive as the search for the first black hole ever formed. Somewhere, hidden in the depths of space and time, lies a cosmic relic, a black hole that was born in the earliest moments after the Big Bang. If we could find it, we might uncover secrets about the first stars, the origins of galaxies, and the very nature of the universe itself. This is the story of an ongoing cosmic hunt, one that could rewrite our understanding of the past and shape our vision of the future. Black holes are among the most enigmatic objects in the universe. They warp space, distort time, and swallow anything that dares to cross their event horizon. Yet, despite their terrifying reputation, they also hold the key to some of the deepest questions in astrophysics. Most black holes we know about today formed from the collapse of massive stars, but the one astronomers are searching for, the first black hole, would be a different kind of entity altogether. It would have emerged when the universe was still in its infancy, during a time when stars were just beginning to form and gravity was shaping the first galaxies. Finding it is no easy task, but the rewards of doing so could be unparalleled. The quest to find the first black hole is based on several key ideas. The early universe was a chaotic place, filled with swirling clouds of primordial gas composed mainly of hydrogen and helium. As gravity pulled this gas together, the first stars ignited, burning hotter and brighter than anything that came after them. These stars, known as population 3 stars, were colossal, hundreds of times the mass of our Sun. They lived fast and died young, collapsing in spectacular explosions that could have left behind the first black holes. But not just any black holes, these would have been the seeds from which the first galaxies grew, influencing the entire structure of the universe. Detecting these ancient black holes is one of the greatest challenges in astronomy. Unlike stars, black holes do not emit light, making them incredibly difficult to observe directly. Instead, scientists must rely on indirect methods, such as looking for the effects of a black hole's immense gravity on nearby objects. One potential way to find the first black hole is by searching for quasars, extremely bright, distant objects powered by supermassive black holes. If we can find a quasar from the very early universe, it might be harboring one of these ancient black holes at its core. Recent discoveries have provided tantalizing hints that such black holes may exist. Observations with powerful telescopes like the James Webb Space Telescope and the Atacama Large Millimeter/Submillimeter Array, ALMA, have revealed quasars that existed when the universe was less than 1 billion years old. Some of these quasars contain black holes with masses of over 1 billion suns, which raises an intriguing question: how did such massive black holes form so quickly? One possibility is that they started as the first black holes, growing rapidly by feeding on gas and merging with other black holes over time. But there is another possibility, one even more mysterious and mind-bending. Some physicists believe that the first black holes might not have come from stars at all. Instead, they could be primordial black holes, objects that formed directly from the dense energy of the early universe. Unlike stellar black holes, which are born from collapsing stars, primordial black holes could have emerged from fluctuations in the fabric of space itself. If these objects exist, they would be some of the oldest structures in the universe, predating even the first stars. The idea of primordial black holes is controversial, but it offers an intriguing solution to several cosmic puzzles. For one, these black holes could help explain dark matter, the invisible substance that makes up most of the mass in the universe. If enough primordial black holes were created in the early universe, they could account for the missing mass that astronomers have been struggling to identify for decades. Additionally, some scientists believe that detecting these black holes could provide insights into the physics of the Big Bang itself, offering a rare glimpse into the moments when time and space, as we know them, first came into existence. So, how do astronomers hope to find the first black hole? One promising approach is gravitational wave astronomy. When black holes merge, they send out ripples in the fabric of spacetime, known as gravitational waves. The Laser Interferometer Gravitational Wave Observatory, LIGO, and other observatories have already detected these waves from more recent black hole collisions, but scientists are now working on new detectors that could sense much older and smaller black holes. If we can detect gravitational waves from a black hole that formed in the first billion years of the universe, it could be the breakthrough we need. Another method involves studying the cosmic microwave background (CMB), the faint radiation left over from the Big Bang. If primordial black holes existed, they would have influenced the way this radiation spread across the early universe. Some researchers are analyzing the CMB for unusual patterns that could indicate the presence of these ancient black holes. In recent years, computer simulations have also played a crucial role in the search. By recreating the conditions of the early universe, scientists can model how the first black holes might have formed and evolved. These simulations suggest that if the first black holes were indeed massive, they would have played a key role in shaping the galaxies we see today. In other words, our own Milky Way might owe its existence to one of these primordial giants. But there are still many unanswered questions. If the first black hole was truly a stellar remnant, then we need to explain how it grew so large so quickly. If it was primordial, then we need to understand how and why such objects formed in the first place. And if we don't find any evidence of these black holes at all, then we might need to rethink our entire understanding of the early universe. The search for the first black hole is not just a scientific endeavor, it is a journey into the unknown, a quest to uncover the secrets of the cosmos. Every new discovery, every new observation, brings us closer to answering one of the most fundamental questions in astronomy. What was the universe like at its very beginning? In the coming years, new telescopes and observatories will push the boundaries of our knowledge even further. The James Webb Space Telescope is already providing unprecedented views of the early universe, while future missions like the Laser Interferometer Space Antenna, LISA, will open new windows into gravitational wave astronomy. As technology advances, so too does our ability to peer deeper into the past, searching for the first black hole that ever formed. This search is not just about understanding black holes, it is about understanding ourselves. By finding the first black hole, we are tracing the origins of everything we see today, from the stars in the night sky to the atoms in our bodies. It is a reminder that the universe is far older and far stranger than we can imagine, and that every discovery brings us closer to answering the ultimate question: where did it all begin? The hunt for the first black hole ever formed is not just about pinpointing a single cosmic object, it is a grand investigation into the fundamental processes that shape the universe. If we can locate this ancient black hole, we might not only confirm our theories about the early universe but also uncover entirely new physics that challenge what we thought we knew about space, time, and matter. One of the biggest challenges in this search is the vast scale of time and distance involved. Light takes billions of years to reach us from the most distant regions of the cosmos, meaning that the deeper we look into space, the further back in time we are seeing. But even with our most powerful telescopes, we are limited by how much detail we can extract from such remote objects. This is why astronomers have turned to alternative methods, such as gravitational lensing, to magnify the distant universe. Gravitational lensing is a phenomenon predicted by Einstein's theory of general relativity. When light from a distant object, such as a quasar, passes near a massive foreground galaxy, the gravity of that galaxy bends and amplifies the light, allowing us to see objects that would otherwise be too faint. Some scientists believe that gravitational lensing could help us spot early black holes by magnifying the regions of space where they might be hiding. If we detect an unusual pattern in the lensed light of a distant quasar, it could indicate the presence of one of these ancient black holes. But even if we find an extremely old quasar, we still face another dilemma: determining whether the black hole at its center is truly among the first ever formed. After all, quasars are powered by supermassive black holes, which are typically millions to billions of times the mass of the Sun. If these black holes started out as the first stellar mass black holes from population 3 stars, they would have had to grow at an extraordinary rate to reach their current size. The question then becomes, is such rapid growth possible? Some researchers propose a mechanism known as direct collapse black holes. Instead of forming from a dying star, these black holes might have originated when enormous clouds of primordial gas collapsed directly into a black hole, skipping the star phase entirely. If this happened, it could explain how some black holes became supermassive in such a short cosmic time span. But proving this theory requires finding a black hole from an era when the first stars were still forming, an incredibly difficult task. Another intriguing approach involves searching for rogue black holes that are not actively feeding on surrounding matter and therefore do not emit detectable radiation. These wandering black holes are nearly invisible, but they can reveal their presence through gravitational microlensing. This occurs when a black hole passes in front of a distant star, temporarily magnifying its light. If we can detect an unusually strong microlensing event that suggests the presence of a primordial or early black hole, it would be one of the most exciting discoveries in modern astrophysics. The search for these elusive black holes is also intertwined with another major cosmic mystery, the nature of dark matter. Dark matter is an invisible substance that makes up roughly 85% of the total matter in the universe, yet we have no direct way of observing it. Some scientists speculate that dark matter could be composed, at least in part, of primordial black holes. If this is true, then our search for the first black hole ever formed could also solve one of the biggest puzzles in physics. To test this idea, astronomers are conducting large-scale sky surveys, such as those using the Vera C. Rubin Observatory. This observatory, set to begin operations soon, will scan the entire sky repeatedly, looking for transient events that might indicate the presence of unseen black holes. If a primordial black hole exists and is moving through space, its gravitational influence should be detectable as it passes in front of background stars and galaxies. Meanwhile, advancements in computational astrophysics are allowing scientists to simulate the evolution of the universe with increasing precision. Supercomputers can now model the formation of the first galaxies, tracing the growth of black holes over billions of years. These simulations provide crucial insights into what we should be looking for in our observational data. If a particular pattern emerges, such as a specific distribution of black holes in the early universe, it could guide future searches and help narrow down where to look. At the heart of this quest is one of the most profound questions in science. How did structure emerge in the universe? Black holes, despite their destructive reputation, played a crucial role in sculpting the cosmos. The first black holes likely acted as anchors for galaxy formation, pulling in gas and dust to create the first galactic structures. Without these early black holes, the universe as we know it might look completely different, or might not have formed at all. But there is another, even more mind-bending possibility. Some physicists believe that black holes could be linked to the multiverse hypothesis, the idea that our universe is just one of many. According to certain models, black holes might not just trap matter, they could act as portals to other universes. If the first black hole ever formed still exists somewhere in the cosmos, could it contain clues about realities beyond our own? This idea is purely speculative for now, but it highlights the vast implications of finding the first black hole. It is not just about understanding the past, it is about unlocking the deepest secrets of existence itself. As technology advances, the search will only intensify. The next generation of space telescopes, such as the Nancy Grace Roman Space Telescope, will provide even deeper views into the distant universe. New gravitational wave detectors, such as the Einstein Telescope and LISA, will allow us to detect black hole mergers that occurred billions of years ago. Each of these instruments brings us one step closer to uncovering the first black hole ever formed. And yet, even with all these advancements, the mystery remains. The universe guards its secrets well, and the answers we seek may still be hidden beyond our current reach. But if history has taught us anything, it is that human curiosity is relentless. Every discovery leads to new questions, and every unanswered question fuels the drive to explore further. One day, perhaps not too far from now, astronomers may finally pinpoint the location of the first black hole. When that moment comes, it will be more than just a scientific triumph, it will be a window into the origins of everything. And in that moment, as we gaze into the depths of space and time, we may finally come face to face with the first echo of the universe's beginning. The search for the first black hole ever formed is not merely an exploration of the past, it is a confrontation with the very nature of reality. Each new piece of data brings with it deeper questions, hinting at forces and structures in the universe that we have yet to understand. If we succeed in identifying this ancient black hole, it could serve as a cosmic time capsule, offering a direct glimpse into the primordial universe as it first emerged from the Big Bang. But what would that black hole look like today? Given the passage of more than 13 billion years, any black hole formed in the early universe would have undergone profound changes. If it remained isolated, it may still exist as a primordial relic, quietly drifting through the cosmos, detectable only through gravitational effects. If, however, it interacted with its environment, it may have grown significantly by accreting matter or merging with other black holes. This raises a fundamental question. Is the first black hole ever formed still distinguishable from the countless other black holes that have since come into existence? One promising avenue of research involves studying the cosmic microwave background, CMB, the faint afterglow of the Big Bang. This radiation has been traveling through space for nearly 14 billion years, carrying with it subtle imprints of the earliest structures in the universe. If the first black holes formed early enough, they could have left detectable distortions in the CMB, revealing their presence through their gravitational influence on surrounding matter. Advanced space observatories, such as the upcoming CMB-S4 experiment, aim to analyze these distortions with unprecedented precision, potentially offering indirect evidence of the first black hole's existence. Another key piece of the puzzle lies in the behavior of the first galaxies. The earliest black holes likely played a crucial role in galactic evolution, providing the gravitational anchor necessary for the formation of the first large-scale cosmic structures. By studying the oldest galaxies we can observe, astronomers hope to trace the footprints of their central black holes and determine whether they align with current theories of black hole formation. If they do not, if we find evidence that black holes existed even before the first galaxies, we may be forced to reconsider how and when these cosmic giants came into being. One particularly tantalizing possibility is that the first black holes were not formed from the collapse of stars but rather from quantum fluctuations in the fabric of spacetime itself. Some models suggest that in the extreme conditions of the early universe, tiny regions of space could have undergone rapid gravitational collapse, creating so-called primordial black holes. Unlike black holes formed from stars, these primordial black holes could have existed mere moments after the Big Bang, making them the oldest structures in the cosmos. If such black holes exist, they could provide a direct link between quantum mechanics and general relativity, the two fundamental yet often contradictory theories that govern our understanding of the universe. Discovering primordial black holes would not only confirm their existence but could also help us unravel the mystery of how gravity behaves at the smallest scales, potentially leading to new insights into quantum gravity and the true nature of spacetime. As we continue our search, we must also consider the possibility that the first black hole may no longer exist in a form we can recognize. Some theories suggest that black holes can evaporate over time through a process known as Hawking radiation. If this is the case, then the first black hole ever formed may have long since vanished, leaving behind only subtle echoes in the structure of the cosmos. However, the rate of Hawking radiation depends on the mass of the black hole, and a sufficiently large black hole could still persist even after billions of years. If the first black hole was of substantial size, it may still be lurking somewhere in the universe, waiting to be discovered. This search is not just about finding a single object, it is about rewriting our understanding of cosmic history. If we can determine how the first black holes formed, we may also unlock the secrets of dark matter, dark energy, and the fundamental forces that shape the universe. The discovery of the first black hole could serve as the missing link in our understanding of how matter and energy interacted in the earliest moments of existence, providing a clearer picture of the forces that set the stage for everything we see today. But beyond the science, there is something deeply profound about this quest. The search for the first black hole is, in many ways, a search for our own origins. It is an attempt to reach back through the eons, to touch the very first structures that emerged in the vast emptiness of the young universe. It is a testament to human curiosity and our relentless drive to explore the unknown, to uncover the deepest truths hidden in the fabric of reality. With every new telescope launched, with every new dataset analyzed, we come closer to solving this mystery. And perhaps one day, in the depths of space, we will find it, the first black hole, a silent witness to the birth of the universe, waiting for us to finally uncover its secrets. The search for the first black hole ever formed is one of the most ambitious and profound scientific quests in human history. It is not just a search for an ancient cosmic object but an attempt to uncover the very mechanisms that shape the universe itself. Every discovery we make about black holes brings us closer to answering some of the deepest questions in physics. How did structure emerge in the early universe? What role did black holes play in the formation of galaxies? Could black holes hold the key to understanding dark matter, dark energy, or even the fundamental nature of reality? To truly grasp the significance of this search, we must go back to the beginning, back to the first few 100 million years after the Big Bang, when the universe was a vastly different place. Unlike today's cosmos, filled with galaxies, stars, and planets, the early universe was a hot, dense sea of hydrogen and helium, with no visible structures. During this time, known as the Cosmic Dark Ages, the universe was essentially featureless, with only slight density variations left over from the Big Bang. These tiny fluctuations in density were crucial, as they provided the seeds from which all cosmic structures would eventually form. One of the prevailing theories is that the first black holes emerged when the first stars, known as population 3 stars, reached the end of their lives. These were unlike any stars that exist today. Since they were made of pure hydrogen and helium, with no heavier elements, they behaved differently from modern stars. They were likely much more massive, with some estimates suggesting they could have reached hundreds of times the mass of the Sun. Because of their extreme size, they burned through their nuclear fuel quickly and exploded as supernovae, leaving behind black holes that were among the first of their kind in the universe. If this is how the first black holes formed, then their discovery would not only confirm our theories about early star formation but also provide crucial insight into the process of black hole growth. Given that some black holes in the early universe reached supermassive sizes in an astonishingly short amount of time, understanding how the first black holes grew is one of the biggest challenges in astrophysics. Did they grow slowly by accreting gas, or did they experience rapid bursts of mass accumulation through collisions and mergers? Another possibility is that the first black holes did not come from stars at all. Some theories suggest that under the extreme conditions of the early universe, massive clouds of primordial gas could have collapsed directly into black holes, skipping the stellar phase entirely. These direct collapsed black holes would have started out much larger than their stellar-born counterparts, potentially explaining how some black holes in the early universe reached supermassive sizes so quickly. If these direct collapsed black holes existed, they could provide key evidence for alternative models of black hole formation. Some scientists even speculate that these black holes might have played a role in shaping the distribution of galaxies, acting as gravitational centers that pulled in matter and influenced the formation of large-scale cosmic structures. This idea challenges our traditional view of galaxy formation, suggesting that black holes may not be merely the byproducts of galaxy growth but rather fundamental building blocks of the universe. But even if we accept that the first black holes formed through stellar collapse or direct collapse, a major challenge remains: finding them. Black holes, by their very nature, do not emit light, making them extremely difficult to detect. However, when they accrete matter, pulling in gas and dust from their surroundings, they can release immense amounts of energy, often outshining entire galaxies. The most powerful of these luminous black holes are known as quasars, and astronomers have already detected quasars that existed within the first billion years of cosmic history. These early quasars are fascinating because they provide direct evidence that massive black holes existed in the early universe. However, they also raise an enormous mystery. How did these black holes grow so large in such a short period of time? The formation of supermassive black holes is still an unsolved problem, and some researchers suggest that the first black holes must have had an unknown mechanism that allowed them to accumulate mass far more quickly than previously thought. One way to solve this mystery is to look even further back, to find black holes that existed before the earliest known quasars. If we can detect black holes that formed only a few 100 million years after the Big Bang, they could provide direct evidence of the very first generation of black holes. This is why astronomers are turning to some of the most powerful telescopes ever built, such as the James Webb Space Telescope, JWST, which is designed to observe the faintest and most distant objects in the universe. JWST is already revolutionizing our understanding of the early cosmos. Its infrared capabilities allow it to peer through cosmic dust and detect the light from galaxies that existed more than 13 billion years ago. If it finds evidence of black holes forming at even earlier times than we expect, it could challenge existing theories of black hole growth and suggest that these objects played a far more significant role in cosmic history than we currently understand. But JWST is only the beginning. Future missions, such as the Nancy Grace Roman Space Telescope and the upcoming generation of gravitational wave detectors, may provide even more precise measurements of the early universe. Gravitational waves, which are ripples in space-time caused by violent cosmic events, could allow us to detect the mergers of early black holes, providing crucial data on their formation and evolution. If we can identify gravitational waves from the first black hole mergers, it would be a direct confirmation that black holes were among the first structures to form in the universe. At the same time, new theoretical models are being developed to explain how the first black holes could have influenced cosmic evolution. Some researchers propose that early black holes may have had an effect on the reionization of the universe, a period when the first light from young galaxies and quasars ionized the surrounding hydrogen gas, making the universe transparent to radiation. If black holes contributed to this process by emitting high-energy radiation, they may have played a more significant role in shaping the structure of the universe than previously thought. Another intriguing possibility is that the first black hole ever formed is not alone. If primordial black holes exist, they may be scattered throughout the cosmos, hidden among the stars and galaxies we observe today. Some of these black holes could even be relatively close to us, wandering undetected through interstellar space. This raises a fascinating question. Could primordial black holes be responsible for some of the unexplained phenomena we see in astronomy? Some scientists have proposed that these ancient black holes might account for a portion of dark matter, the mysterious substance that makes up the majority of the universe's mass but does not emit light. If even a small fraction of dark matter consists of primordial black holes, it would revolutionize our understanding of the cosmos and provide a direct link between the earliest moments of the universe and the large-scale structures we see today. Ultimately, the search for the first black hole ever formed is about more than just finding a single object. It is about uncovering the cosmic forces that shaped everything we know. Whether it is hidden in the distant reaches of the universe, lurking undetected in interstellar space, or leaving its imprint on the cosmic microwave background, its discovery would be one of the most significant breakthroughs in the history of astrophysics. As technology advances and our observational techniques improve, we are closer than ever to answering the question that has fascinated scientists for decades. Where is the first black hole, and what can it tell us about the universe? The answers may lie just beyond our reach, waiting for the next great discovery to bring them into the light. The search for the first black hole ever formed continues to push the boundaries of our understanding of the universe. As telescopes and detection methods become more advanced, astronomers are increasingly confident that they will soon uncover definitive evidence of these ancient cosmic giants. But the implications of this discovery go far beyond simply identifying the first black hole. If we succeed, we could rewrite our understanding of cosmic evolution, black hole physics, and even the nature of spacetime itself. One of the most promising methods for detecting these ancient black holes is through gravitational lensing. Gravitational lensing occurs when the immense gravity of a massive object, such as a black hole, bends and magnifies the light from distant galaxies behind it. If primordial black holes, or the first stellar black holes, exist in sufficient numbers, their gravitational influence should be detectable in large-scale sky surveys. The Vera C. Rubin Observatory, set to begin full operations in the near future, will scan vast portions of the sky with unparalleled precision. By analyzing lensing effects, astronomers may be able to identify black holes that formed in the earliest epochs of the universe. Another key observational tool is the study of ultra-faint dwarf galaxies. These small, ancient galaxies contain some of the oldest stars in the universe and are believed to have formed soon after the first generation of black holes. If the first black holes played a significant role in shaping the early cosmos, their fingerprints may still be visible in the structure and behavior of these dwarf galaxies. By closely analyzing their dynamics, astronomers hope to infer the presence of ancient black holes that could date back to the universe's infancy. But beyond direct observations, theoretical physics also plays a crucial role in this search. Some of the greatest mysteries surrounding black holes involve the fundamental nature of space-time and gravity itself. If the first black holes formed through exotic processes, such as quantum fluctuations in the fabric of space, then they could provide a bridge between quantum mechanics and general relativity. This connection is at the heart of one of the biggest unresolved problems in modern physics: the quest for a theory of quantum gravity. One of the most intriguing theories suggests that the first black holes could have been formed by collapsing regions of space with unusually high energy densities. If this is true, then the study of these black holes could offer insights into the earliest moments of the universe, potentially revealing unknown physics that existed before the first stars were born. Some researchers even propose that black holes could be tied to extra dimensions or unknown particles, providing a link between black hole formation and the hidden fabric of reality. The role of dark matter in black hole formation is another avenue of exploration. While dark matter remains one of the greatest mysteries in cosmology, some theories suggest that it may have clumped together in the early universe in ways that encouraged the rapid formation of black holes. If this is the case, then discovering the first black hole could also provide indirect evidence about the nature of dark matter, what it is, how it interacts with normal matter, and how it shaped the universe's large-scale structure. Of course, there is also the possibility that the first black hole ever formed is still out there, wandering through the vastness of space, undetected. Rogue black holes that do not reside at the center of galaxies, but instead drift freely through intergalactic space, are thought to exist in large numbers. If the first black hole formed in a location where it was not surrounded by enough material to accrete and grow, it may have remained relatively small and inconspicuous, making it one of the most challenging objects to detect. To locate such an object, astronomers are considering new techniques, such as detecting the subtle distortions in starlight caused by a rogue black hole passing in front of distant stars. This method, known as microlensing, could provide one of the best chances to find an ancient black hole that is not actively consuming matter. Upcoming space missions, such as the European Space Agency's Euclid telescope, are expected to provide high-resolution data that may reveal evidence of these hidden objects. But as we continue this search, we must also consider the possibility that the first black hole has already disappeared. Hawking radiation, the theoretical process by which black holes slowly evaporate over time, suggests that smaller black holes could eventually dissipate, releasing their energy back into the universe. If the first black hole was relatively small, it may no longer exist in any detectable form, leaving behind only subtle imprints in the cosmic fabric. However, even if the first black hole has long since vanished, the knowledge gained from this search will be invaluable. Each discovery along the way brings us closer to answering some of the deepest questions in astrophysics. Whether we find the first black hole directly, detect its gravitational influence, or uncover new insights into black hole formation, this journey is reshaping our understanding of the cosmos. Ultimately, the search for the first black hole ever formed is about more than just one object. It is about understanding the very forces that shaped our universe. It is a quest that connects the past to the present, linking the earliest moments of existence to the structures we see today. And as our technology improves and our knowledge expands, we are closer than ever to solving one of the greatest cosmic mysteries of all time. The search for the first black hole ever formed is not just about identifying a single object. It is a journey into the very origins of the universe itself. If we can find evidence of these ancient black holes, we may unlock some of the deepest secrets about how the cosmos evolved in its earliest moments. But to do that, astronomers must overcome immense observational and theoretical challenges. One of the biggest hurdles in this quest is the sheer difficulty of detecting black holes that existed billions of years ago. Unlike stars, which emit light, black holes do not shine on their own. They are only visible when they actively consume matter, generating intense radiation in the process. However, the first black holes may have formed in environments with very little material to consume, making them nearly invisible to conventional telescopes. This means that astronomers must rely on indirect methods, such as studying their gravitational effects, to detect them. One promising technique involves analyzing the cosmic microwave background (CMB), the faint glow left over from the Big Bang. If the first black holes existed during the earliest epochs of the universe, they may have left imprints in the structure of the CMB. Some researchers believe that these imprints could reveal how and when the first black holes formed, as well as provide clues about their size and distribution. By studying minute variations in the CMB, astronomers hope to uncover signals that could lead them to the first black holes. Another potential clue lies in the distribution of heavy elements in the universe. The first black holes may have played a key role in enriching their surroundings with elements such as carbon, oxygen, and iron. If early black holes consumed matter and then released powerful outflows of energy, they could have influenced the formation of the first galaxies. By studying the chemical composition of ancient stars, astronomers may be able to trace the influence of the first black holes on their environments. Meanwhile, theoretical physicists are considering radical new ideas about how the first black holes may have formed. Some propose that they could be linked to exotic processes in the early universe, such as the collapse of high-energy fluctuations left over from the Big Bang. Others suggest that the first black holes may not have formed from dying stars at all, but instead emerged from dense regions of dark matter. If this is the case, then the discovery of these ancient black holes could provide new insights into the nature of dark matter itself. The role of black holes in shaping cosmic structure is another key question in this search. If the first black holes formed early enough, they may have acted as seeds for the growth of galaxies. The immense gravity of these black holes could have drawn in gas and dust, triggering the formation of stars and planetary systems. Some simulations even suggest that without these early black holes, galaxies like the Milky Way may never have formed at all. If we can confirm the existence of these primordial black holes, we may gain a deeper understanding of how the large-scale structure of the universe emerged. But even as we search for the first black hole, we must also confront the possibility that our understanding of black hole formation may need to be revised. Some alternative theories suggest that what we think of as black holes may not be singularities at all, but instead something entirely different. Hypothetical objects such as gravastars or fuzzballs have been proposed as alternatives to traditional black holes, challenging our assumptions about what happens at the edge of spacetime. If the first black hole ever formed turns out to be something else entirely, it could revolutionize our understanding of gravity and quantum physics. As new telescopes and space missions come online, the chances of solving this mystery increase. The James Webb Space Telescope, with its ability to see deep into the infrared spectrum, is already providing new insights into the early universe. Future missions, such as the Laser Interferometer Space Antenna, LISA, will detect gravitational waves from distant cosmic events, potentially revealing new clues about the first black holes. By combining multiple observational methods, astronomers are assembling a more complete picture of how black holes formed and evolved over cosmic time. Ultimately, the search for the first black hole ever formed is about more than just answering a single question. It is about understanding the fundamental forces that shape the universe. Whether these black holes formed from dying stars, collapsing dark matter, or exotic quantum processes, their discovery will have profound implications for astrophysics, cosmology, and fundamental physics. If we do find the first black hole, it will be one of the most significant discoveries in the history of astronomy. It will provide a window into the earliest moments of the universe, shedding light on how matter and energy behaved under extreme conditions. It may even help us bridge the gap between general relativity and quantum mechanics, bringing us closer to a unified theory of physics. But even if the first black hole remains elusive, the search itself is pushing the boundaries of human knowledge. With each new observation and theoretical breakthrough, we are unraveling the mysteries of black holes and their role in shaping the cosmos. And as we look deeper into space and further back in time, we may one day uncover the ultimate origins of these enigmatic objects, unlocking a cosmic story that began billions of years ago. The search for the first black hole ever formed is not just a scientific pursuit, it is a journey into the origins of the cosmos itself. If we can find this ancient black hole, we may unlock some of the most profound secrets of the universe, from the nature of dark matter and cosmic inflation to the birth of galaxies and the evolution of spacetime. Every piece of new data, every refined observation, and every breakthrough in theoretical physics brings us closer to uncovering the existence of the first black hole and understanding the cosmic forces that shaped everything we see today. One of the most exciting possibilities is that the first black hole may not have been a single, isolated object but rather part of a population of primordial black holes, PBHs. These hypothetical black holes would have formed in the early universe, long before the first stars. If PBHs exist, they could be scattered throughout space, hiding in galaxies, floating in intergalactic voids, or even making up a portion of the dark matter that dominates the cosmos. Detecting these black holes is a monumental challenge, but scientists are developing new methods to identify their presence. One promising approach is looking for microlensing events, where a black hole passing in front of a distant star momentarily magnifies the star's light. If primordial black holes are common, surveys like those conducted by the Vera C. Rubin Observatory and the upcoming Nancy Grace Roman Space Telescope should detect these lensing effects over time. Another method involves searching for gravitational wave signals from mergers between ancient black holes. The Laser Interferometer Space Antenna, LISA, set to launch in the 2030s, will detect low-frequency gravitational waves that current ground-based observatories like LIGO and Virgo cannot pick up. If the first black holes ever formed are still merging today, they may produce unique gravitational wave signatures that could tell us about their origins. Additionally, astronomers are studying the cosmic infrared background to identify any unusual heat signatures left over from the early universe. If the first black holes were consuming gas and dust billions of years ago, they may have produced radiation that still lingers today. By mapping faint infrared signals across the sky, scientists hope to detect indirect evidence of these ancient black holes. Theoretical physics also plays a crucial role in this search. Some researchers believe that the first black holes could provide insights into physics beyond the standard model, potentially revealing unknown particles or new forces of nature. If primordial black holes formed from quantum fluctuations in the early universe, they could be tied to ideas like string theory or the multiverse. In this sense, discovering the first black hole could be more than just a step forward in astrophysics. It could revolutionize our understanding of the fundamental nature of reality itself. Another intriguing possibility is that the first black hole is still out there, hidden in plain sight. Rogue black holes, those that are not bound to any galaxy, may be drifting through intergalactic space, undetectable unless they happen to pass in front of a bright background object. If such a black hole exists, it may be waiting for the right observational technique to be discovered before revealing itself. Some researchers even speculate that an ancient black hole could be lurking on the outskirts of our own solar system, possibly influencing the orbits of distant objects in the Kuiper belt. While this idea remains speculative, it highlights just how much we still have to learn about the unseen universe. Despite these challenges, the search for the first black hole continues to advance at a rapid pace. Every new telescope and observational technique brings us closer to solving this mystery. Whether we find the first black hole through gravitational waves, cosmic background radiation, microlensing events, or some other method yet to be conceived, its discovery will fundamentally alter our understanding of the universe's first moments. This search is not just about finding a single object. It is about unlocking a deeper understanding of the cosmos. The first black hole ever formed is a relic of a time when the universe was vastly different from today, a time when the first structures were taking shape and the fundamental laws of physics may have behaved in ways we do not yet fully understand. Whether it formed from the collapse of the first stars, the direct collapse of dense gas clouds, or exotic quantum fluctuations, its existence holds the key to some of the biggest questions in science. As technology improves and our observational reach extends further into the universe, the chances of discovering this ancient black hole increase. With each new study, each new telescope, and each new theoretical breakthrough, we are unraveling the story of the first black holes and their role in shaping the cosmos. And perhaps, in the near future, we will finally uncover the first black hole ever formed, shedding light on the deepest mysteries of existence itself. The search for the first black hole ever formed is one of the most profound scientific endeavors of our time. It is not just about discovering a single ancient object, but about unraveling the very fabric of cosmic history. If we can detect this first black hole, we will gain unparalleled insight into the origins of the universe, the nature of gravity, and the processes that govern the formation of the first cosmic structures. But this search is fraught with challenges, requiring advanced technology, innovative observational techniques, and a deeper understanding of the fundamental physics that govern the cosmos. To appreciate the difficulty of this search, we must first consider the nature of black holes themselves. Unlike stars, black holes do not emit light, they absorb it. This makes them incredibly difficult to detect unless they are actively consuming matter, producing high-energy emissions in the process. The first black hole ever formed likely existed in an environment that was very different from today's universe, one in which there may have been little material available for accretion. As a result, it may have remained silent for billions of years, evading direct detection. One of the most promising ways to find the first black holes is by studying the cosmic microwave background, CMB, the faint radiation left over from the Big Bang. If primordial black holes existed in the early universe, they may have influenced the structure of the CMB in subtle ways. Tiny variations in temperature and density across the CMB could hold clues to their presence, offering indirect evidence of these ancient objects. Scientists are using high-resolution CMB maps, such as those provided by the Planck satellite, to search for these potential signatures. Future missions, such as NASA's upcoming CMB-S4 experiment, aim to achieve even greater sensitivity, potentially revealing new insights about the first black holes. Another approach involves looking at the distribution of heavy elements in the universe. The first black holes, if they formed early enough, could have played a significant role in enriching their surroundings with metals such as carbon, oxygen, and iron. When black holes consume matter, they release powerful radiation and outflows of energy that can alter the chemical makeup of nearby gas clouds. By studying ancient stars, particularly those in the halos of galaxies, astronomers may be able to detect unusual chemical signatures that hint at the influence of the first black holes. Some researchers believe that the first black holes may have been significantly more massive than those formed from stellar collapse today. These so-called direct collapse black holes could have formed from massive clouds of primordial hydrogen that collapsed under their own gravity without forming stars first. If such black holes existed, they would have grown rapidly, influencing the formation of early galaxies. Some of the most distant quasars, extremely bright, energetic objects powered by supermassive black holes, may be the descendants of these early black holes. Studying the properties of ancient quasars could help us understand whether the first black holes formed via direct collapse or through more conventional means. Gravitational waves provide yet another method for detecting the first black holes. When two black holes merge, they create ripples in spacetime that travel across the universe. The Laser Interferometer Gravitational Wave Observatory, LIGO, and its European counterpart, Virgo, have already detected dozens of black hole mergers, some of which involve unexpectedly large black holes. If the first black holes ever formed still exist and continue to merge, they may produce unique gravitational wave signals. Future observatories such as the Laser Interferometer Space Antenna, LISA, which will operate in space, could detect these signals with even greater precision, potentially revealing the presence of black holes that formed in the first moments of the universe. There is also the possibility that the first black holes were not formed through conventional astrophysical processes at all. Some theories suggest that primordial black holes could have originated from quantum fluctuations in the early universe. During the first fraction of a second after the Big Bang, the universe underwent a rapid expansion known as inflation. If certain regions of space had slightly higher densities than others, they could have collapsed into black holes almost immediately. If these primordial black holes exist, they could provide a natural explanation for dark matter, the mysterious, unseen substance that makes up most of the mass in the universe. Detecting these black holes could also shed light on physics beyond the standard model. If primordial black holes formed from exotic quantum processes, their existence could provide evidence for new particles or even extra dimensions of space. Some speculative theories suggest that these black holes could be linked to microscopic wormholes or other exotic phenomena that challenge our current understanding of spacetime. In this sense, finding the first black hole ever formed could open entirely new avenues of research, leading to breakthroughs in both astrophysics and fundamental physics. Despite the many challenges, the search for the first black hole is accelerating. Next-generation telescopes such as the James Webb Space Telescope, JWST, are capable of peering deep into the early universe, capturing light from some of the first galaxies. By studying these galaxies, astronomers hope to identify signs of early black holes shaping their formation. The Square Kilometre Array, SKA, a massive radio telescope currently under construction, will be able to detect faint radio signals from the early universe, potentially revealing new information about the first black holes and their environments. Even if we do not find the first black hole in the near future, the search itself is invaluable. Every observation, every theoretical model, and every new experiment pushes the boundaries of our knowledge. Whether the first black holes formed from dying stars, direct gas collapse, quantum fluctuations, or an unknown process entirely, their discovery will revolutionize our understanding of the cosmos. Ultimately, the search for the first black hole is about more than just astrophysics. It is about uncovering the origins of the universe itself. These ancient objects hold the key to understanding how galaxies formed, how gravity behaves under extreme conditions, and even how the fundamental forces of nature came into existence. If we can find the first black hole, we will be taking a giant leap toward answering some of the most profound questions in science. Where did we come from? How did the universe evolve? And what forces shaped the cosmos in its earliest moments? With every new breakthrough, we move closer to solving this cosmic mystery. Whether through gravitational waves, high-energy observations, or new theoretical insights, the discovery of the first black hole is within our reach. And when we finally find it, the implications will be nothing short of revolutionary, changing our understanding of the universe forever. The search for the first black hole ever formed is not merely an exercise in astrophysics. It is a quest to understand the deepest origins of the universe. To find this elusive object is to peer into the very fabric of cosmic history, to uncover the earliest moments of structure formation, and to explore the fundamental nature of spacetime itself. It is a challenge that demands the most advanced telescopes, the most precise measurements, and the most daring theoretical models. As we push the boundaries of observation and physics, we may finally unravel the mysteries surrounding the first black hole and its role in shaping the cosmos. One of the central challenges in this search is determining exactly when and how the first black hole could have formed. The universe was born from the Big Bang approximately 13.8 billion years ago. For the first few 100,000 years, it was a hot, dense plasma where photons could not travel freely. This period, known as the photon-baryon fluid era, ended when the universe cooled enough for atoms to form, allowing light to travel freely. The cosmic microwave background (CMB) that we detect today is the relic of this transition. But in the vast cosmic timeline, the first black holes would not have formed until later, during an era known as the Cosmic Dark Ages. The Cosmic Dark Ages began roughly 380,000 years after the Big Bang and lasted until the first stars ignited. During this time, the universe was filled with neutral hydrogen and helium, but no visible light sources. It was a time of growing density fluctuations. Regions with slightly higher mass concentrations slowly drew in surrounding matter through gravity. These regions would eventually collapse to form the first stars and, potentially, the first black holes. There are multiple competing theories about how the first black hole could have emerged. The most conventional explanation is that it formed from the collapse of the very first massive star. These first-generation stars, known as population 3 stars, were vastly different from the stars we see today. They were composed almost entirely of hydrogen and helium, as heavier elements had not yet been forged in stellar cores. Lacking metals, these stars were unable to regulate their temperatures as efficiently as modern stars, leading them to grow far more massive. Some estimates suggest that population 3 stars could have been hundreds of times the mass of the Sun. When these enormous stars reached the end of their lives, they may have undergone direct collapse into black holes, bypassing the supernova explosion stage entirely. If this occurred, then the first black hole would have been born as a seed black hole, with an initial mass ranging from a few tens to a few hundred times the mass of the Sun. Over cosmic time, this seed black hole could have accreted surrounding gas and merged with other black holes, growing into a supermassive black hole millions or even billions of times the Sun's mass. This could explain how the enormous black holes powering distant quasars formed so early in cosmic history. However, there is another possibility, one that suggests the first black hole may have formed not from a star, but directly from primordial conditions in the early universe. This idea is known as the direct collapse black hole model. In this scenario, regions of gas in the early universe collapsed under their own gravity without forming stars first, leading to the rapid formation of extremely massive black holes. This would allow supermassive black holes to appear much earlier than if they had to grow slowly from smaller stellar mass black holes. Some of the oldest quasars we have observed, such as those existing less than a billion years after the Big Bang, suggest that black holes must have formed rapidly, lending support to the direct collapse model. Yet another hypothesis posits that the first black hole may not have originated from astrophysical processes at all, but rather from exotic physics at play in the earliest moments of the universe. If tiny fluctuations in the density of the early universe were extreme enough, some regions of space could have collapsed into black holes almost immediately after the Big Bang. These so-called primordial black holes would have formed within the first second of cosmic history, making them far older than any black hole created by stellar collapse. Primordial black holes are especially intriguing because they could solve one of the greatest mysteries in physics, the nature of dark matter. Astronomers know that dark matter makes up roughly 85% of the universe's total mass, but its exact nature remains unknown. Some researchers propose that primordial black holes could account for at least some of this missing mass, lurking undetected in the vastness of space. If even a fraction of dark matter consists of primordial black holes, then the first black hole ever formed may still be out there, hidden among these ancient relics. Finding the first black hole requires an entirely new approach to observation. Because black holes do not emit light, they can only be detected indirectly, either by their gravitational effects on surrounding matter or through emissions from material falling into them. One promising strategy is to search for black hole microlensing events, where a black hole passes in front of a distant star and temporarily magnifies its light. If primordial black holes exist in significant numbers, we should be able to detect these lensing events in future sky surveys. Another approach involves gravitational waves. When black holes merge, they release powerful ripples in spacetime that can be detected by observatories like LIGO and Virgo. If primordial black holes exist, their mergers may produce unique gravitational wave signals that could reveal their origins. Future space-based detectors such as the Laser Interferometer Space Antenna, LISA, will be able to detect these signals with even greater sensitivity, potentially identifying the first black holes ever formed. Radio astronomy may also play a crucial role in this search. The Square Kilometre Array, SKA, currently under construction, will be the most powerful radio telescope ever built, capable of detecting faint signals from the cosmic dark ages. By studying the distribution of neutral hydrogen during this time, astronomers may be able to infer the presence of early black holes as they ionize surrounding gas. The implications of discovering the first black hole would be profound. Not only would it confirm our models of early structure formation, but it could also provide new insights into the nature of gravity itself. Black holes are the ultimate testing grounds for Einstein's general relativity, and detecting an ancient black hole could reveal whether our current theories of gravity hold up under the extreme conditions of the early universe. Furthermore, if the first black hole was a primordial black hole, it could force us to rethink the entire history of cosmic evolution. It might suggest that black holes predated galaxies, and that they played a fundamental role in shaping the large-scale structure of the universe. It could even open the door to new physics, perhaps hinting at extra dimensions, quantum gravity effects, or unknown forms of matter. As technology advances, our chances of finding this first black hole increase dramatically. Upcoming observatories such as the James Webb Space Telescope, JWST, the Extremely Large Telescope, ELT, and future gravitational wave detectors will allow us to probe deeper into the early universe than ever before. With each new discovery, we move one step closer to answering one of the most fundamental questions in cosmology. How did the first black hole form, and what does it tell us about the origins of the universe? The search continues, and with every new piece of evidence, we edge closer to uncovering the truth. Whether the first black hole was born from a dying star, a collapsing gas cloud, or a quantum fluctuation in the primordial universe, its discovery will change our understanding of the cosmos forever. The answer may be hidden in the depths of space, waiting for us to find it. And when we do, it will be one of the greatest achievements in the history of science. As the search for the first black hole ever formed continues, astronomers are faced with a daunting challenge. How do you detect something that has been hidden for billions of years, lurking in the cosmic shadows? The first black hole may not shine like a quasar, nor produce an easily recognizable signal. It may be isolated, without an accretion disk to light it up. It may have drifted through space undetected for eons, escaping our telescopes. And yet, despite these obstacles, scientists are developing new techniques to track down this elusive relic of the early universe. One of the most promising approaches is looking for the imprints left by the first black holes on their surroundings. Even if a black hole itself cannot be seen, the effects it has on nearby matter and spacetime can be. If the first black hole was a seed that grew into a supermassive black hole, it would have played a key role in the formation of the first galaxies. Its immense gravitational pull would have attracted gas, triggering the birth of stars and shaping the structure of the galaxy around it. By studying the oldest known galaxies, astronomers may be able to infer the presence of an ancient black hole at their center. Some of the most distant quasars, powered by supermassive black holes billions of times the Sun's mass, are already providing clues about the rapid growth of black holes in the early universe. If these quasars existed only a few 100 million years after the Big Bang, it means their black holes must have formed and grown incredibly quickly. This suggests that the first black holes formed much earlier than previously thought, possibly within the first few million years after the Big Bang. If so, then the first black hole could still be out there, a silent witness to the universe's earliest moments. The next generation of telescopes will be crucial in this search. The James Webb Space Telescope, JWST, which is designed to observe the infrared light from the early universe, is already providing new insights into the first galaxies and black holes. But JWST alone may not be enough to find the first black hole. It will take an even more powerful instrument to detect the faintest and most ancient black holes. The upcoming Extremely Large Telescope, ELT, with its massive 39-meter mirror, will be able to peer deeper into space than any ground-based telescope before it. It will allow astronomers to study the formation of black holes in unprecedented detail. Another key tool in the search is the study of high-energy radiation. If the first black hole was actively consuming matter, it would have released X-rays, which could have left detectable imprints on the cosmic background radiation. The Athena X-ray Observatory, set to launch in the 2030s, will be able to scan the sky for faint X-ray sources that could be ancient black holes. By mapping out the distribution of these X-ray sources, scientists may be able to trace the growth of black holes from the earliest times. But what if the first black hole wasn't a stellar remnant, or a direct collapsed black hole? What if it was a primordial black hole, formed in the first seconds after the Big Bang? If primordial black holes exist, they could provide a completely different way of looking at the early universe. Unlike black holes formed from stars, primordial black holes would not have required any previous structure to exist. They could have formed directly from quantum fluctuations in the early universe. detecting primordial black holes is an entirely different challenge. Since they do not emit light, they can only be found through their gravitational effects. One possibility is using gravitational lensing, where a black hole bends the light of a background star. If a primordial black hole passes in front of a distant star, it could temporarily magnify its light, revealing its presence. Large-scale sky surveys, such as those conducted by the Vera C. Rubin Observatory, will be scanning millions of stars, looking for these subtle distortions. Another way to detect primordial black holes is through their mergers. If these black holes have been drifting through space for billions of years, they may occasionally collide and merge, sending out ripples in space-time. The Laser Interferometer Space Antenna, LISA, a future space-based gravitational wave detector, will be able to detect these signals, potentially identifying black holes that formed in the first moments of the universe. The discovery of the first black hole would be a breakthrough in multiple fields of physics. It would help resolve one of the biggest questions in cosmology: how did the first structures in the universe form? It could also provide insights into quantum gravity, the elusive theory that unifies general relativity with quantum mechanics. Black holes are natural laboratories for testing extreme physics, and an ancient black hole could reveal whether our current theories of gravity hold up under the most extreme conditions. Moreover, if the first black hole turns out to be a primordial black hole, it could revolutionize our understanding of dark matter. Some researchers have proposed that dark matter might not be made of exotic particles but rather of countless tiny black holes left over from the early universe. If this is the case, then the search for the first black hole might also be the search for the missing mass of the universe. As technology advances and our observational techniques improve, we are getting closer than ever to finding this ancient cosmic relic. The answer may lie in the depths of space, in the faintest signals detected by our most powerful telescopes. Or it may be hidden in the ripples of space-time, waiting to be revealed by future gravitational wave observatories. Whatever the case, the discovery of the first black hole will be one of the most significant moments in the history of science. The search continues, and with each new observation, we move closer to unlocking one of the greatest mysteries of the cosmos. Whether the first black hole was born from the death of a primordial star, the collapse of a gas cloud, or the quantum fluctuations of the infant universe, its discovery will change our understanding of the cosmos forever. And when we finally find it, we will have taken one more step toward answering the ultimate question: where did it all begin? If the first black hole is ever found, it will redefine our understanding of cosmic history. The implications of such a discovery stretch far beyond mere astronomy. It will challenge our current theories of how structure in the universe evolved, how black holes formed and grew, and even the fundamental laws of physics themselves. But to locate this ancient relic, astronomers must overcome some of the most difficult observational challenges ever faced. One of the biggest problems is the sheer remoteness of the first black hole. If it formed shortly after the Big Bang, it would be more than 13 billion light-years away. This means its light, or rather, the light of anything it influenced, would have traveled for almost the entire age of the universe before reaching us. But looking that far back in time presents a unique issue. The early universe was filled with dense hydrogen gas that absorbed much of the radiation from the first celestial objects. This cosmic fog complicates our ability to see anything clearly from that time period. However, there is a potential way around this problem. If the first black hole grew rapidly by accreting gas, it would have heated up the surrounding environment, creating a bubble of ionized gas. This process, known as reionization, left fingerprints on the cosmic microwave background radiation, the afterglow of the Big Bang. Scientists believe that by analyzing subtle variations in this radiation, they may be able to infer the presence of the first black holes, even if they cannot be observed directly. Another way to track down the first black hole is by looking for signs of its gravitational influence on other objects. Even if it has remained isolated for billions of years, its immense gravity would still have had an impact on surrounding matter. Astronomers are searching for unusual patterns in the motion of stars in ancient galaxies, looking for evidence of a hidden, unseen mass that could be an ancient black hole. But what if the first black hole is not at the edge of the visible universe, but much closer? Some theories suggest that primordial black holes, if they exist, could still be floating around the universe today. These ancient black holes would be nearly impossible to detect, as they would not emit any light. However, their presence could be revealed through gravitational lensing, when their gravity bends and magnifies the light from a distant object. By carefully analyzing distortions in the light from faraway stars and galaxies, astronomers hope to identify wandering primordial black holes that have survived since the dawn of time. There is also the possibility that the first black hole may be found through its gravitational waves. When two black holes merge, they send ripples through spacetime that can be detected by observatories like LIGO and Virgo. If a black hole from the early universe were to collide with another black hole today, it could produce a signal unlike any other detected before. The upcoming Laser Interferometer Space Antenna, LISA, a space-based gravitational wave detector, will be able to search for these signals, potentially revealing the presence of black holes that have existed for billions of years. The discovery of the first black hole would have profound implications for our understanding of physics. One of the biggest mysteries in modern science is how supermassive black holes grew so quickly in the early universe. If the first black hole was a direct collapse black hole, it could help explain how some black holes reached enormous sizes in such a short time. On the other hand, if it was a primordial black hole, it could challenge our understanding of the early universe and even provide clues about the nature of dark matter. Some researchers believe that primordial black holes could make up a significant portion of dark matter, the invisible substance that makes up most of the universe's mass. If this theory is correct, then finding the first black hole could also solve one of the biggest mysteries in cosmology. Instead of being made of exotic particles, dark matter could simply be a collection of tiny black holes formed in the first moments after the Big Bang. No matter where or how the first black hole formed, its discovery would be a milestone in human knowledge. It would confirm the existence of objects that predate the first galaxies and provide new insights into the physics of the early universe. More than that, it would give us a glimpse into a time when the cosmos was still in its infancy, just beginning to take shape. As technology advances and new observatories come online, we are getting closer than ever to answering this ultimate cosmic mystery. The search for the first black hole is not just about finding a single object. It is about understanding the origins of everything we see in the universe today. It is a quest that takes us back to the very beginning, to the birth of time itself. The search for the first black hole ever formed is more than a scientific endeavor. It is a journey into the origins of the cosmos itself. Every black hole we observe today, whether stellar mass or supermassive, is a descendant of some earlier generation of black holes. But where did it all begin? If we can locate the first black hole, we might finally understand the mysterious chain of events that led to the universe as we know it. One of the major questions scientists are grappling with is whether the first black hole was a result of stellar collapse or something more exotic, like a primordial black hole. If it was formed from a collapsing star, that means the first generation of stars must have already existed and died by the time this black hole was born. But how fast did the first stars live and die? Were they massive enough to collapse directly into black holes, bypassing the supernova stage? These questions drive the search for the universe's oldest black holes, as they hold the key to understanding the life cycles of the very first stars. Astronomers believe that the earliest stars, known as population 3 stars, were very different from the stars we see today. These stars were composed almost entirely of hydrogen and helium, with virtually no heavier elements. This made them much more massive than modern stars. Some may have been hundreds of times the mass of the Sun. Because of their enormous size, these first-generation stars would have burned through their fuel quickly, living only a few million years before collapsing. If one of these stars collapsed directly into a black hole without a supernova explosion, it could have created the first black hole in the universe. But what if the first black hole didn't come from a star at all? The idea of primordial black holes suggests that some black holes may have formed just moments after the Big Bang. In the earliest fraction of a second, the universe was an extremely dense and chaotic place, with fluctuations in energy and matter. Some of these fluctuations may have been so intense that they created regions of space dense enough to collapse into black holes. Unlike stellar black holes, These primordial black holes would not require stars to form. They would have come into existence almost immediately, making them the true first black holes. If primordial black holes exist, they could have profound implications for our understanding of dark matter. Scientists have long theorized that dark matter is made of an unknown type of particle. But what if it is actually made of tiny black holes? If the first black hole ever formed was a primordial black hole, then there could be countless others like it, drifting through the universe unnoticed. Detecting these objects would not only confirm their existence but also provide a new perspective on one of the greatest mysteries in physics. Finding the first black hole is an enormous challenge, but new technology is making it possible to probe deeper into the universe's history than ever before. The James Webb Space Telescope, JWST, is already revealing some of the earliest galaxies and black holes ever observed. Its infrared capabilities allow it to peer through the cosmic dust and see objects from a time when the universe was only a few 100 million years old. However, even JWST may not be powerful enough to detect the very first black hole. It will likely require even more advanced instruments in the future. One promising approach is using gravitational waves to detect ancient black holes. When two black holes merge, they produce ripples in spacetime that can be detected by observatories like LIGO and Virgo. If we detect a black hole merger that dates back to the earliest period of the universe, it could reveal the existence of black holes that have existed since the dawn of time. Future space-based gravitational wave detectors, such as LISA, Laser Interferometer Space Antenna, will be even more sensitive to these signals and may help us uncover the first black holes. Another approach involves looking for the effects of black holes on the cosmic microwave background, CMB, radiation. If early black holes were actively feeding on gas, they would have emitted high-energy radiation that could have left detectable imprints on the CMB. By carefully analyzing variations in the CMB, scientists hope to find indirect evidence of ancient black holes. The discovery of the first black hole would be a monumental moment in astronomy, not only because it would confirm theories about black hole formation but also because it would provide insights into the evolution of the universe. If the first black hole was a stellar mass black hole, it would tell us that stars were forming and dying incredibly early in cosmic history. If it was a primordial black hole, it would force us to reconsider everything we know about the early universe, inflation, and dark matter. Regardless of how or when it formed, the first black hole is out there, hidden somewhere in the vast expanse of space. It has existed for billions of years, silently drifting through the cosmos or anchoring the earliest galaxies. Its discovery will not only unlock secrets about the past but also help us predict the fate of black holes in the distant future. As our telescopes become more powerful, our gravitational wave detectors more sensitive, and our understanding of physics more refined, we are getting closer to solving one of the greatest mysteries of all time. The search for the first black hole is not just about finding an object, it is about understanding the very fabric of the universe itself. The search for the first black hole ever formed is one of the most ambitious quests in modern astrophysics. It is a search that stretches the limits of our technology, our understanding of physics, and our ability to look back in time to the earliest moments of the universe. The discovery of this black hole would answer some of the most profound questions about cosmic evolution. How did black holes first emerge? Did they play a role in shaping the early universe? Could they be the missing link in our understanding of dark matter? One of the greatest challenges in this search is the immense distance between us and the first black holes. If a black hole formed shortly after the Big Bang, it would now be more than 13 billion light-years away. That means the light, or more precisely, the radiation, from anything related to this black hole has been traveling across the cosmos for nearly the entire age of the universe. To observe something this ancient, astronomers must look at objects so far away that their light is only now reaching Earth. The further back we look, the closer we get to the first black hole, but that also means dealing with unique obstacles that make detection difficult. One major problem is the nature of the early universe itself. During the first few 100 million years after the Big Bang, the cosmos was filled with a dense fog of neutral hydrogen gas, which absorbed much of the radiation emitted by the first stars and black holes. This period, known as the Cosmic Dark Ages, makes direct observation of early black holes incredibly challenging. However, astronomers have developed ways to work around this limitation by searching for indirect evidence of early black holes. One such method involves looking for ionization bubbles, regions of space where intense radiation from the first black holes and stars stripped electrons from hydrogen atoms, creating transparent patches in the cosmic fog. The presence of such bubbles in the early universe suggests that something was producing high-energy radiation, and an early black hole could be the culprit. The James Webb Space Telescope, JWST, is currently examining these ancient regions, searching for signs of reionization that might hint at the presence of early black holes. Another technique is gravitational lensing, which occurs when a massive object bends and magnifies the light from objects behind it. If the first black hole formed in an early galaxy, its immense gravity may have distorted the light from background stars and galaxies in ways we can detect today. By analyzing these distortions, astronomers hope to identify the gravitational fingerprint of the first black hole. Even more intriguing is the possibility that the first black hole might not be hidden in the depths of space but much closer to us. Some theories suggest that primordial black holes, formed directly from density fluctuations in the early universe, could still exist today. Unlike black holes that form from collapsing stars, primordial black holes would have been present from the very beginning, meaning they could be scattered throughout the cosmos. If these objects exist, they might occasionally pass in front of distant stars, briefly magnifying their light in an effect known as microlensing. By carefully monitoring stars in our galaxy, astronomers hope to catch a glimpse of a passing primordial black hole, which could provide crucial insights into the earliest moments of the universe. A more direct approach to finding the first black hole involves detecting gravitational waves, ripples in space-time caused by massive objects in motion. The merger of two early black holes would have produced powerful gravitational waves, which might still be detectable today. Current observatories like LIGO and Virgo are already detecting gravitational waves from relatively recent black hole mergers, but future space-based detectors, such as the Laser Interferometer Space Antenna, LISA, will be sensitive enough to detect mergers that occurred billions of years ago. If we find evidence of an ancient black hole merger, it could provide the first direct clue about the earliest black holes. There is also the possibility that the first black hole played a significant role in galaxy formation. Some theories suggest that supermassive black holes existed even before the first galaxies had fully formed. If this is the case, then black holes may have acted as seeds around which the first galaxies grew. The discovery of an early black hole at the center of a primitive galaxy would support this idea, suggesting that black holes were fundamental to the structure of the universe from the very beginning. Understanding the nature of the first black hole could also help answer one of the biggest questions in cosmology: what is dark matter? Despite making up most of the universe's mass, dark matter has never been directly detected. Some researchers speculate that if primordial black holes exist, they could account for at least some of the missing dark matter. If we find evidence that the first black hole was primordial, it could revolutionize our understanding of what dark matter is and how it shaped the universe. The discovery of the first black hole would have profound implications for physics as well. It would allow scientists to test Einstein's theory of general relativity in an environment never before observed, one that is billions of years older than any black hole we have studied so far. If discrepancies between theoretical predictions and observational data emerge, it could hint at new physics beyond our current understanding. Despite the difficulties in detecting the first black hole, optimism remains high. The rapid advancement of telescopes, gravitational wave detectors, and computational models means that we are closer than ever to uncovering this cosmic mystery. New space observatories, such as the upcoming Nancy Grace Roman Space Telescope, will be equipped with advanced infrared imaging capabilities that may help pinpoint the oldest black holes. Future radio telescopes, like the Square Kilometre Array, SKA, could also provide crucial data on how the earliest black holes interacted with their surroundings. As astronomers continue their search, they remain guided by a simple yet profound question: where did black holes come from? The answer lies in the depths of the universe, hidden within the echoes of its earliest moments. Whether it is found through gravitational waves, light distortions, or unexpected clues in the cosmic microwave background, the first black hole is waiting to be discovered. The search for the first black hole is not just about finding an ancient relic, it is about understanding the birth of the universe itself. If and when we find it, we will gain an unprecedented window into the conditions of the early cosmos, the formation of galaxies, and perhaps even the nature of space-time itself. Until then, the search continues, pushing the boundaries of human knowledge ever further into the unknown. The search for the first black hole ever formed is more than just the pursuit of a single ancient object, it is a journey into the very origins of the cosmos. If we can locate this black hole, we will gain insight into the earliest conditions of the universe, the formation of the first stars and galaxies, and perhaps even the fundamental nature of space-time itself. But as astronomers continue their search, they face one of the greatest challenges in modern science. How do you find something that has been hidden for nearly the entire history of the universe? To understand the first black hole, we must consider the chaotic environment in which it may have formed. Shortly after the Big Bang, the universe was a hot, dense soup of particles, light, and energy. As it expanded and cooled, the first atoms formed, and eventually, matter began clumping together under the influence of gravity. The first stars, known as population 3 stars, ignited within these primordial clouds of gas, marking the beginning of the first cosmic structures. These first stars were likely enormous, many times more massive than the Sun, and burned through their fuel at a rapid pace. Because they lacked heavier elements, their internal structures were different from modern stars, allowing them to grow larger and live shorter lives. Within just a few million years, an instant on cosmic timescales, many of them would have reached the end of their lifespans. If they were massive enough, they could have collapsed directly into black holes without even going supernova, leaving behind the universe's first black hole. But what if the first black hole was even older than the first stars? Some scientists propose that black holes could have formed within the first second of the universe's existence, long before stars, galaxies, or even atoms had fully emerged. These so-called primordial black holes could have been created by extreme density fluctuations in the fabric of spacetime itself. If such black holes exist, they could still be lurking in the universe today, either as tiny relics or as the seeds of some of the supermassive black holes we observe in modern galaxies. The idea that primordial black holes might still exist is particularly exciting because it could help explain one of the biggest mysteries in physics: dark matter. For decades, astronomers have observed that galaxies appear to contain far more mass than we can see. This missing mass is known as dark matter, and while most theories suggest it is made of unknown subatomic particles, some researchers believe it could actually be made of tiny black holes that formed in the earliest moments of the universe. If this is the case, then the first black hole ever formed might not be a single object at the edge of the observable universe. It might be part of a vast, hidden population of ancient black holes that still influence the cosmos today. Detecting such objects would require new observational techniques, such as searching for their gravitational effects on stars or looking for signs of their influence on the cosmic microwave background radiation. One of the most promising ways to find the first black hole is through gravitational waves. These ripples in spacetime are produced when massive objects collide or interact, and they carry information about some of the most extreme events in the universe. If an ancient black hole merged with another object billions of years ago, the resulting gravitational waves might still be detectable today. Instruments like LIGO, Virgo, and future space-based detectors like LISA could pick up signals from these ancient mergers, providing indirect evidence of the first black holes. Another potential clue comes from the cosmic microwave background (CMB), the afterglow of the Big Bang. If early black holes existed, they would have influenced the radiation left over from the birth of the universe. By studying tiny fluctuations in the CMB, scientists might be able to identify patterns that hint at the presence of early black holes, offering a glimpse into the conditions of the cosmos when they first formed. The James Webb Space Telescope, JWST, is another key tool in the search for ancient black holes. Its ability to observe extremely distant galaxies allows it to peer back in time to when the universe was only a few 100 million years old. If it detects unusually bright, compact sources of light in the early universe, those could be signs of black holes actively consuming matter. Finding such objects could confirm that black holes existed at a much earlier stage than previously thought. If the first black hole was part of a forming galaxy, it could also have played a crucial role in shaping that galaxy's evolution. Some scientists believe that early black holes may have helped drive the formation of galaxies by acting as gravitational anchors, pulling gas and stars together to form the first galactic structures. If this theory is correct, then finding the first black hole might also mean identifying one of the first galaxies, providing even more insight into the early universe. Despite these promising avenues of research, the search for the first black hole remains one of the most difficult challenges in astronomy. The universe has changed dramatically over the past 13.8 billion years, and many of the early structures that once existed have long since been destroyed or transformed. The signals we are searching for may be faint, buried beneath layers of cosmic history, requiring ever more sophisticated technology to uncover. But scientists remain optimistic. Every year, new telescopes, detectors, and computer models bring us closer to answering this fundamental question. The discovery of the first black hole will not only rewrite our understanding of cosmic history, but may also lead to entirely new physics, forcing us to rethink what we know about gravity, space-time, and the very nature of reality itself. As we continue this quest, we are reminded that black holes are not just objects of scientific study, they are windows into the deepest mysteries of the universe. Whether they formed from the first collapsing stars or emerged from the quantum chaos of the early cosmos, the first black hole represents the beginning of a story that continues to unfold with every new discovery. The universe has kept this secret for billions of years, but with each passing decade, we come closer to unlocking it. The first black hole ever formed is out there, waiting to be found. And when we finally discover it, we may not only learn about the past, we may uncover the key to understanding the entire universe itself. If we are to find the first black hole ever formed, we must push the limits of our observational technology to detect objects that are billions of light years away. The farther we look into space, the further back in time we see, and identifying a black hole from the cosmic dawn will require detecting signals from the earliest moments of the universe. While telescopes like the James Webb Space Telescope have already begun revealing unprecedented details of ancient galaxies, the challenge of detecting a black hole that has existed since the first stars formed is far greater than simply looking at a distant galaxy. Black holes themselves are invisible. They do not emit light, nor do they reflect it. Their presence is only inferred through their effects on nearby matter. This means that the search for the first black hole must focus on detecting the indirect signs of its existence: gravitational lensing, energetic radiation from accretion disks, or the gravitational waves it may have produced. One of the best ways to find ancient black holes is by studying quasars. These are supermassive black holes at the centers of galaxies that are actively consuming matter, creating incredibly bright emissions. Quasars are some of the brightest objects in the universe, visible from billions of light years away. If we can find quasars that existed less than a billion years after the Big Bang, it would suggest that black holes must have formed even earlier, possibly from the first generation of stars or from direct collapse mechanisms. Astronomers have already detected quasars that date back to when the universe was just 600 million years old. These quasars harbor black holes with masses of over a billion times that of the Sun, raising a perplexing question: how did black holes grow so large in such a short amount of time? The existence of these quasars suggests that black holes must have formed rapidly after the Big Bang, possibly through mechanisms we do not yet fully understand. One hypothesis is that these early black holes did not form from stars at all, but rather from the direct collapse of massive gas clouds. In the early universe, the conditions may have allowed entire regions of gas to collapse directly into black holes without first forming a star. This process could have created massive black holes much earlier than expected, which then continued to grow by accreting surrounding material. If this theory is correct, then the first black hole ever formed may have been born in the first few 100 million years after the Big Bang, or possibly even earlier. Another possibility is that small primordial black holes, if they existed, merged together to create larger ones. If tiny black holes formed in the chaotic conditions of the early universe, Some of them could have merged over time, gradually growing into the enormous black holes we observe in ancient quasars. Detecting evidence of these primordial black holes would require searching for signs of their mergers, which may have left detectable imprints in the cosmic microwave background or produced gravitational waves that could still be detected today. Recent advancements in gravitational wave astronomy offer another promising avenue for detecting the first black hole. The Laser Interferometer Gravitational Wave Observatory, LIGO, and the Virgo Interferometer have already detected mergers of black holes, proving that these objects collide and combine over time. But these observations mostly involve black holes that formed in more recent cosmic history. Future space-based detectors, like the Laser Interferometer Space Antenna, LISA, will be capable of detecting gravitational waves from black hole mergers that took place billions of years ago. If LISA detects an unusually old merger signal, it could provide crucial evidence for the first black holes in the universe. Additionally, some scientists propose that the first black holes could have left traces in the cosmic structure of the universe itself. If early black holes influenced the formation of galaxies, we might be able to detect patterns in the large-scale distribution of matter that point to their presence. Some simulations suggest that galaxies that formed around early black holes may have distinct characteristics compared to those that formed through more conventional means. By studying the oldest known galaxies, astronomers might uncover subtle clues that reveal the influence of ancient black holes. The search for the first black hole also has profound implications for our understanding of physics. Current theories of black hole formation rely on Einstein's general relativity, but there are still many unanswered questions about how black holes behave under extreme conditions. If we discover black holes that formed earlier than our current models predict, it could challenge our understanding of gravity and lead to new theories that extend beyond Einstein's equations. One of the most mysterious aspects of black holes is what happens at their core. According to general relativity, the center of a black hole contains a singularity, a point of infinite density where the laws of physics break down. But many physicists suspect that something deeper is at play. Some theories suggest that singularities may not exist at all, and that black holes might be hiding new physics that could help us understand quantum gravity. If we find an ancient black hole and study its properties, it might provide clues about these unresolved questions. Another fascinating possibility is that the first black holes could be connected to the idea of cosmic inflation, the rapid expansion of the universe in its earliest moments. Some theories suggest that quantum fluctuations during this period could have created small black holes, which then served as the seeds for the larger black holes we see today. If this is the case, finding the first black hole might not just tell us about black holes themselves, it could reveal details about the physics of the Big Bang itself. Despite the immense challenges, astronomers remain hopeful that the first black hole will be found. With new telescopes, improved simulations, and the ability to detect gravitational waves, we are entering an era where the most ancient cosmic mysteries may finally be uncovered. The search for the first black hole ever formed is not just a quest to find a single object, it is a journey into the fundamental nature of the universe. It is a search for the remnants of the first stars, the origins of galaxies, and the deepest laws of physics. Whether the first black hole was born from the collapse of the first stars, the direct collapse of massive gas clouds, or the violent conditions of the Big Bang itself, its discovery will reshape our understanding of the cosmos. And so, the search continues. With every new observation, with every new gravitational wave detection, with every new discovery from deep space telescopes, we come closer to uncovering the truth about the first black hole. Somewhere in the vast universe, hidden in the depths of cosmic time, lies the answer to one of the greatest mysteries of all. As we push further into the unknown, the search for the first black hole ever formed is not just a matter of looking into the deep past, it is a race against time itself. The further back we look, the fainter the signals become, and the more difficult it is to distinguish between what was once there and what has been erased by billions of years of cosmic evolution. Yet, with each breakthrough in observational astronomy, we are getting closer to answering the ultimate question: when did the first black hole form, and what does its existence tell us about the nature of the universe? One of the greatest challenges in this search is the fact that black holes do not emit light. They are, by definition, regions of space where gravity is so strong that nothing, not even light, can escape. This makes direct observation nearly impossible. Instead, astronomers must rely on indirect evidence, looking for signs of their influence on nearby matter or detecting the radiation emitted by matter as it falls into them. But in the case of the first black hole, this task is even more difficult. If it formed in the earliest moments of the universe, it may not have had time to gather surrounding material, meaning it could have remained almost entirely invisible. However, some theoretical models suggest that the first black hole may not have been entirely silent. If it formed from the collapse of the first stars, it would have been surrounded by gas that, as it fell into the black hole, could have emitted powerful bursts of radiation. These bursts, known as high-energy X-rays or gamma rays, might have left an imprint on the cosmic microwave background, the faint radiation left over from the Big Bang. Some researchers believe that by carefully studying variations in this ancient radiation, we may be able to detect the indirect signature of the first black holes. Another possibility is that the first black hole played a role in the reionization of the universe. During the first few 100 million years after the Big Bang, the universe was filled with a dense fog of neutral hydrogen gas that absorbed most forms of light. It was only when the first stars and black holes formed that this fog was gradually cleared in a process known as reionization. If the first black holes were actively feeding on surrounding material, they could have emitted high-energy radiation that contributed to this transformation of the universe. By studying the timing and pattern of reionization, astronomers hope to uncover evidence of these ancient black holes. Some theories suggest that the first black hole may not have been a stellar remnant at all, but rather a primordial black hole, an object that formed directly from the energy fluctuations of the Big Bang itself. If primordial black holes existed, they could have ranged in size from tiny microscopic objects to massive giants far larger than the black holes formed from collapsing stars. Some physicists even speculate that such black holes could still exist today, potentially making up a fraction of the mysterious dark matter that pervades the universe. If we were to find evidence of a primordial black hole that dates back to the beginning of time, it would not only be the first black hole ever formed, it could also solve one of the greatest mysteries in modern physics. One way to detect these elusive objects is through gravitational lensing. When a black hole passes in front of a distant star or galaxy, its gravity can bend and magnify the light from the background object. If primordial black holes are scattered throughout the universe, their gravitational lensing effects could be observed, providing indirect evidence of their existence. Some studies have already searched for these effects, but so far, no conclusive evidence of primordial black holes has been found. However, future telescopes with even greater sensitivity may finally be able to detect them. Another promising approach comes from the field of gravitational wave astronomy. If the first black hole ever formed merged with another black hole at some point in the early universe, it would have sent ripples through space-time, gravitational waves, that could still be detectable today. While current gravitational wave detectors like LIGO and Virgo are primarily sensitive to recent black hole mergers, future space-based observatories like LISA, Laser Interferometer Space Antenna, could detect signals from much earlier in cosmic history. If we were to detect a gravitational wave signature from a black hole merger that occurred billions of years ago, it could provide direct evidence of the first black holes. The search for the first black hole is also intertwined with the question of how black holes grow. The supermassive black holes we see today, with masses millions or even billions of times that of the Sun, must have started as much smaller objects. But how did they grow so rapidly? Did they form through the gradual accumulation of matter over billions of years, or did some process allow them to reach immense sizes almost immediately? If we can find one of the first black holes and determine its mass, it could provide critical clues about this growth process. One of the biggest mysteries in this search is the apparent paradox of supermassive black holes existing when the universe was still young. The discovery of quasars with black holes over 1 billion times the mass of the Sun, just 600 million years after the Big Bang, suggests that black holes can grow much faster than our current theories predict. This raises the question: could the first black hole have been much larger than we expect? If so, what mechanism allowed it to form? Some researchers believe that direct collapse black holes, objects that formed not from stars but from the direct collapse of vast clouds of gas, could explain the rapid growth of these ancient black holes. If we find the first black hole and it turns out to be far more massive than expected, it could provide strong evidence for this theory. Despite these challenges, the tools available to astronomers today are more powerful than ever before. The James Webb Space Telescope, launched with the goal of studying the earliest galaxies, may provide key insights into this search. By detecting faint signals from the first billion years of cosmic history, it could reveal clues about the conditions that allowed the first black holes to form. Other upcoming observatories, such as the Square Kilometre Array, SKA, will revolutionize our ability to study the early universe in radio wavelengths, potentially uncovering new signals from the first black holes. The implications of finding the first black hole extend far beyond astronomy. Black holes are one of the greatest testing grounds for the laws of physics, and their study has already led to groundbreaking discoveries about relativity, quantum mechanics, and the nature of space and time. If we find evidence that black holes formed even earlier than expected, it could challenge our understanding of gravity itself. Some theories suggest that black holes could provide insights into the unification of general relativity and quantum mechanics, potentially unlocking the secrets of a long-sought theory of quantum gravity. At the heart of this search lies one of the most profound questions in science: what was the universe like in its earliest moments? By finding the first black hole, we are not only uncovering the origins of these enigmatic objects, we are peering into the fundamental processes that shape the cosmos itself. Whether the first black hole was born from a dying star, a collapsing gas cloud, or the quantum fluctuations of the Big Bang, its discovery will mark a milestone in our quest to understand the universe. The search is far from over. Every new observation, every new theoretical breakthrough, and every new technological advance brings us one step closer to finding the first black hole ever formed. And when that moment finally comes, it will not only be a triumph of science, it will be a window into the deepest mysteries of existence itself. The search for the first black hole ever formed is not just about discovering an ancient cosmic relic. It is about unraveling the story of the universe itself. Every black hole carries a hidden history, an imprint of the conditions of the universe at the time it was born. By finding the first black hole, we could answer some of the deepest questions in astrophysics. How did the first structures in the universe form? What role did black holes play in shaping galaxies? And most intriguingly, could black holes hold the key to understanding the fundamental nature of reality? One of the most pressing mysteries in this search is the apparent contradiction between the age of the universe and the existence of massive black holes in its early stages. The most distant quasars, hyperluminous objects powered by supermassive black holes, have been detected at redshifts greater than 7, meaning they existed when the universe was less than 1 billion years old. Yet, according to standard black hole growth models, it should take far longer for a black hole to reach such enormous sizes. This paradox suggests that either black holes formed far earlier than we expect, or they had a way to grow far more quickly than our current theories allow. One possible explanation is the existence of seed black holes that formed through direct collapse. In most cases, black holes are thought to form from the deaths of massive stars. However, in the early universe, conditions may have been different. Instead of forming from stars, some black holes may have arisen from the direct collapse of enormous gas clouds, bypassing the supernova stage entirely. These direct collapse black holes could have started with masses hundreds or even thousands of times that of the Sun, allowing them to rapidly grow into the supermassive black holes we see today. If we can detect one of these early black holes, it would provide strong evidence that this process was at work in the primordial universe. Another intriguing possibility is that black holes grew rapidly through a process known as super-Eddington accretion. Normally, there is a theoretical limit to how fast a black hole can consume material, known as the Eddington limit. If matter falls in too quickly, the intense radiation pressure from the infalling material pushes outward, slowing down the growth. However, some models suggest that under extreme conditions, black holes may have been able to exceed this limit, growing at an extraordinary rate. If the first black hole we find is much larger than expected for its age, it could be evidence that black holes can grow faster than previously thought. A different approach to finding the first black hole involves looking at the effects black holes had on their surroundings. While black holes themselves do not emit light, they dramatically influence the space around them. If the first black holes existed in the early universe, they would have emitted powerful radiation as they devoured nearby gas and dust. This radiation would have heated the surrounding intergalactic medium, affecting the way light from the first stars was absorbed and re-emitted. By studying the fingerprints of this process in the cosmic microwave background and the large-scale structure of the universe, scientists may be able to infer the presence of these ancient black holes. One of the most promising avenues for detecting these signals is the study of 21 cm radiation. Neutral hydrogen emits a faint signal at this wavelength, which can be used to map the distribution of matter in the early universe. If the first black holes were actively feeding, they would have created distinctive patterns in this radiation. Upcoming radio telescopes like the Square Kilometre Array, SKA, will be capable of detecting these patterns, potentially revealing the presence of the first black holes. Gravitational waves offer another potential pathway to discovering the first black hole. Black holes do not exist in isolation. They often merge with one another in violent cosmic collisions. These mergers create ripples in space-time known as gravitational waves, which can travel across billions of light-years to reach us. If the first black holes formed early enough, some of them may have merged soon after, producing gravitational wave signals that could still be detectable today. Current detectors like LIGO and Virgo can only detect relatively recent black hole mergers, but future observatories like the Laser Interferometer Space Antenna, LISA, will be able to detect much older and more distant signals. If LISA picks up a gravitational wave signature from an extremely ancient black hole merger, it could provide direct evidence of the first black holes. One of the most speculative yet fascinating ideas is that the first black hole might not have been formed through conventional means at all, but rather could have originated from the very fabric of space-time itself. Some theories suggest that during the extreme conditions of the early universe, tiny fluctuations in energy density could have collapsed into black holes almost instantly. These so-called primordial black holes would have formed mere fractions of a second after the Big Bang, and could still exist today. If primordial black holes do exist, they might even account for some or all of the mysterious dark matter that makes up most of the universe's mass. Detecting a primordial black hole would revolutionize physics. Not only would it confirm that black holes could form without the need for stars, but it would also provide direct insight into the physics of the Big Bang itself. There are several ways we might be able to find them. If primordial black holes are small enough, they could slowly evaporate over billions of years due to Hawking radiation, a theoretical process in which black holes lose mass over time. If a primordial black hole is in its final stages of evaporation, it could release a burst of high-energy radiation that might be detectable with gamma-ray telescopes. Alternatively, if primordial black holes are more massive, they could be detected through their gravitational effects. For instance, if a primordial black hole were to pass between us and a distant star, its gravitational field could temporarily magnify the star's light in an effect known as microlensing. Some ongoing surveys, such as the OGLE project, are actively searching for these microlensing events, hoping to catch a glimpse of a primordial black hole. The possibility that the first black hole ever formed could be a primordial black hole also raises profound questions about the nature of black holes themselves. If black holes can form from something other than collapsing stars, it suggests that they are more fundamental to the structure of the universe than we previously thought. Some physicists even propose that black holes could be connected to the fundamental building blocks of reality, possibly related to ideas in quantum gravity and string theory. Despite all these theories and potential detection methods, the truth is that we still don't know when or how the first black hole formed. It could be hiding in the depths of the early universe, its signal buried beneath layers of cosmic noise. It could be something we never expected, an object so strange that it challenges our entire understanding of physics. But one thing is certain: the search for the first black hole is one of the most important scientific endeavors of our time. Every new telescope, every new observation, and every new technological advance brings us one step closer to finding the answer. Whether it is through gravitational waves, X-ray emissions, 21-centimeter radiation, or some other yet-to-be-discovered phenomenon, the first black hole is waiting to be found. And when we do find it, it will not only change our understanding of black holes but also reshape our understanding of the universe itself. The first black hole is not just a point in history. It is a gateway to the past, a key to the future, and a mystery that will push the boundaries of human knowledge. The search continues, and with it, the promise of uncovering one of the greatest secrets the cosmos has ever hidden. The search for the first black hole ever formed continues to push the boundaries of modern astrophysics. Each new technological advancement brings us closer to uncovering this elusive cosmic relic, yet with every discovery, new questions arise. If the first black holes formed earlier than expected, what does that tell us about the physics of the early universe? Could they have played a role in shaping the very structure of the cosmos? And if primordial black holes exist, what implications would that have for our understanding of dark matter, gravity, and even the fundamental nature of spacetime itself? One of the most intriguing aspects of this search is that black holes are, by definition, invisible. They do not emit light, and their presence can only be inferred by the way they interact with their surroundings. This makes detecting the first black hole particularly challenging. Astronomers must rely on indirect signals, X-ray bursts, gravitational waves, and radio emissions to find clues about their existence. The question is, which of these signals will provide the first real evidence? One possibility is that the first black hole may be found through its interaction with the cosmic web, the vast structure of filaments, voids, and galaxy clusters that define the large-scale structure of the universe. In the early universe, matter was not evenly distributed. Instead, tiny fluctuations in density led to the formation of the first stars and galaxies. If the first black holes formed early enough, they would have begun influencing their surroundings, pulling in gas and dust and emitting intense radiation. This process, known as feedback, could have played a crucial role in the evolution of the cosmos. The energy released by growing black holes, particularly in the form of X-rays and ultraviolet radiation, would have affected the temperature and ionization state of the intergalactic medium. By analyzing patterns in the cosmic microwave background (CMB) and mapping the distribution of ionized gas in the early universe, scientists may be able to detect the fingerprints of the first black holes. Future telescopes like the James Webb Space Telescope (JWST) and the upcoming Extremely Large Telescope (ELT) will provide unprecedented detail in studying these ancient signals. However, there is another approach, one that bypasses traditional observations of light and instead focuses on the fundamental warping of spacetime itself. Gravitational wave astronomy, still in its infancy, may hold the key to detecting the first black holes. Unlike electromagnetic radiation, which can be blocked by dust and gas, gravitational waves travel unimpeded through space and time. If the first black holes formed in the chaotic early universe, they would have merged and produced strong gravitational wave signals. Advanced detectors like the Laser Interferometer Space Antenna, LISA, and next-generation terrestrial observatories may be able to capture these signals, offering a direct glimpse into the universe's first moments. The possibility of finding the first black hole also raises profound questions about the nature of black holes themselves. Traditionally, black holes are thought to be simple objects, defined only by their mass, spin, and charge, a principle known as the no-hair theorem. However, some physicists argue that black holes may carry additional information, possibly even remnants of the material they consumed. If this is true, then the first black hole could hold clues about the earliest states of matter, energy, and even the quantum nature of gravity. In the search for the first black hole, some researchers are turning to exotic physics for answers. Theoretical models suggest that under extreme conditions, black holes might not be entirely black. Some alternative theories propose that instead of a singularity, the core of a black hole could contain a region of highly compressed exotic matter, or even a doorway to another universe. While these ideas remain speculative, detecting an ancient black hole could provide critical evidence for or against such theories. Another fascinating possibility is that black holes may have existed before the Big Bang itself. Some theories of cyclic or bouncing universes suggest that black holes could have survived a previous cosmic era, carrying information from an earlier phase of existence. If we were to detect an ancient black hole that predates known cosmic structures, it would challenge everything we understand about the origin of the universe. Despite the challenges, the search for the first black hole is one of the most exciting frontiers in modern science. As technology advances, our ability to peer deeper into the cosmos will improve, bringing us closer to solving this great mystery. Whether through gravitational waves, high-energy radiation, or some yet undiscovered method, the first black hole is waiting to be found. And when it is, it will not only rewrite the history of the universe, it will redefine our understanding of reality itself. The search for the first black hole ever formed continues to challenge our understanding of the cosmos. Each new discovery reveals deeper layers of complexity in the early universe, and astronomers are now exploring multiple avenues to uncover this elusive relic. From the earliest stars and galaxies to the very fabric of space-time itself, the hunt for the universe's first black hole is not just about finding a single object, it's about deciphering the fundamental nature of reality. One of the biggest questions surrounding the first black hole is how quickly it could have formed. Traditional models suggest that black holes emerge from the deaths of massive stars, collapsing under their own gravity. However, this process takes time. The first stars, known as population 3 stars, had to form, live out their lives, and then collapse into black holes. But if the first black holes were detected very early in cosmic history, this would suggest an alternative formation mechanism, one that bypasses the standard stellar life cycle. Some theories propose that the first black holes could have formed directly from collapsing clouds of primordial gas. These so-called direct collapse black holes, DCBHs, would have skipped the star phase entirely, forming massive black holes within just a few 100 million years after the Big Bang. If such black holes existed, they could have been the seeds of the supermassive black holes we see at the centers of galaxies today. The challenge is finding evidence of their existence. To detect a direct collapse black hole, astronomers must look for signs of extreme gravitational influence on its surroundings. One possibility is that these early black holes accreted matter at incredibly high rates, producing powerful radiation signatures. The James Webb Space Telescope, JWST, is expected to be instrumental in identifying such objects by looking for telltale infrared emissions from the earliest galaxies. If an early black hole is actively feeding, it should leave a distinct imprint on the intergalactic medium, which JWST and future observatories could detect. Another possibility is that the first black holes might have formed from the collapse of exotic matter rather than normal gas. Some theories suggest that in the extremely high-energy conditions of the early universe, unusual states of matter, such as quark-gluon plasma or even primordial Higgs fields, could have collapsed directly into black holes. This would open an entirely new realm of physics, suggesting that black holes could have originated from processes beyond standard stellar collapse. The existence of primordial black holes, a separate category of ancient black holes that may have formed in the first moments after the Big Bang, further complicates the search. Unlike black holes formed from dying stars, primordial black holes could have emerged from density fluctuations in the early universe. If true, they could account for some or even all of dark matter. Detecting a primordial black hole would not only confirm an entirely new class of objects, but could also solve one of the biggest mysteries in modern physics: the nature of dark matter. One way to detect these ancient black holes is through gravitational lensing. If a black hole passes in front of a distant star or galaxy, its gravity bends and magnifies the light from the background object. This effect, known as microlensing, could reveal the presence of otherwise invisible black holes. Upcoming space telescopes, like the Nancy Grace Roman Space Telescope, will conduct wide-field surveys that may capture such microlensing events, potentially uncovering the first black holes ever formed. Gravitational waves also offer a promising method of detection. If two of these early black holes merged, the resulting collision would send ripples through space-time. The Laser Interferometer Space Antenna, LISA, a future space-based gravitational wave detector, is expected to be sensitive enough to detect black hole mergers from the early universe. If LISA detects a merger signal that predates known galaxies, it could provide definitive proof of the first black holes. However, one of the greatest challenges in this search is distinguishing between different types of early black holes. If an ancient black hole is detected, how can astronomers determine whether it formed from a dying star, a collapsing gas cloud, or a primordial quantum fluctuation? The answer lies in the details of its mass, spin, and environment. Primordial black holes are expected to have a very different mass distribution compared to black holes formed from stars. They may also behave differently in terms of their interaction with surrounding matter. Furthermore, if the first black hole is detected and appears more massive than expected, this would raise profound questions about how black holes grow. Conventional theories suggest that black holes grow slowly, accumulating mass over billions of years. But if the first black hole is already large in the early universe, it may indicate that black holes can grow much faster than previously thought, perhaps through rapid direct collapse mechanisms, or even exotic physics beyond the standard model. Another mystery is whether these ancient black holes could have influenced the formation of galaxies themselves. If black holes existed before the first galaxies, they might have played a role in structuring the early universe. Some simulations suggest that early black holes could have acted as gravitational anchors, pulling together gas clouds that later formed galaxies. If this is true, then black holes were not just a product of galaxy formation, they were a driving force behind it. Moreover, if the first black holes are found, they could provide clues about the fundamental nature of space and time. Some theories suggest that black holes may store information about the universe's past states and their event horizons. If an ancient black hole still exists, it could carry imprints of the earliest conditions of the cosmos, potentially even traces of physics from before the Big Bang. This touches on deep theoretical questions about whether black holes can encode information about their origins, and whether Hawking radiation might eventually reveal their secrets. As astronomers continue their search, the discovery of the first black hole will be a defining moment in astrophysics. It will confirm or challenge our current understanding of black hole formation, the evolution of the early universe, and even the nature of reality itself. Whether detected through X-rays, gravitational waves, microlensing, or some yet undiscovered method, the first black hole represents a gateway to understanding the origins of everything we see today. With every technological advancement, we are getting closer to solving this cosmic mystery. The next generation of telescopes and space observatories will peer deeper into the universe than ever before, bringing us to the brink of discovery. And when the first black hole is finally found, it will not only be a glimpse into the past, it will be a revelation about the very nature of existence. The search for the first black hole ever formed is not just an astrophysical puzzle, it is a profound inquiry into the origins of the cosmos. As we continue to push the boundaries of observation and theory, every new discovery reshapes our understanding of how black holes emerged, evolved, and influenced the formation of galaxies and large-scale cosmic structures. But what happens when we finally detect this elusive object? What implications will it have for our understanding of the universe? And could it reveal fundamental truths about the nature of reality itself? One of the most intriguing aspects of this search is the potential link between the first black holes and the formation of supermassive black holes, SMBHs. These behemoths, which sit at the centers of galaxies, including our Milky Way, possess masses millions or even billions of times that of the Sun. The origin of SMBHs remains one of the greatest unsolved mysteries in astrophysics. If black holes take billions of years to grow, how did SMBHs reach such enormous sizes within just a few 100 million years after the Big Bang? The discovery of the first black hole could help answer this question. One possibility is that the first black holes served as the seeds for these supermassive giants. If a primordial black hole or a direct collapse black hole formed early in the universe and grew rapidly, it could have provided the foundation for the massive objects we see today. Observing the first black hole could reveal whether SMBHs formed from the gradual accretion of gas and mergers over time, or if they emerged from a more exotic process. If the first black hole is found and turns out to be significantly more massive than expected, it would indicate that black holes can grow much faster than current models predict. This could point to a more efficient mode of accretion, where black holes can consume matter at rates far exceeding the Eddington limit, the theoretical maximum at which a black hole can accumulate mass without blowing away surrounding gas due to radiation pressure. Some exotic models propose that in the early universe, conditions may have allowed for super Eddington accretion, where black holes grew at extreme speeds due to dense and chaotic environments. Another possibility is that early black holes grew rapidly through frequent mergers. The early universe was much denser than it is today, meaning that black holes may have collided and merged far more often than they do in the modern era. If gravitational wave detectors like LISA can pick up signals from these early mergers, they could provide a direct observational record of how the first black holes grew. If such mergers were common, it could mean that SMBH is assembled from a network of smaller black holes that formed in the first few 100 million years. But what if the first black hole doesn't fit any of our existing models? If it is detected and its properties defy current theories, it could mean that black holes are not as simple as we think. The Standard Model describes black holes as singularities surrounded by event horizons, with all information about their formation erased except for mass, spin, and charge. However, some physicists believe that black holes may retain traces of their origins in subtle ways. If an ancient black hole carries any observable characteristics that reveal how it formed, it could challenge the no-hair theorem and force us to rethink fundamental aspects of black hole physics. One of the most groundbreaking possibilities is that the first black hole could provide evidence for physics beyond Einstein's theory of general relativity. While general relativity has been remarkably successful in describing the behavior of black holes, it is incomplete. It breaks down at the singularity, where gravity becomes infinite. Some theories, such as string theory and loop quantum gravity, suggest that the singularity might not actually exist. Instead, the core of a black hole could be made of something else entirely, such as a quantum bridge to another universe, a firewall of high-energy particles, or a region of exotic matter that resists total collapse. If the first black hole exhibits anomalies, such as unexpected radiation patterns, deviations from expected spin rates, or unusual gravitational effects, it could provide the first observational clues that general relativity needs to be replaced or modified. This would be one of the most significant breakthroughs in modern physics, potentially leading to a new unified theory of gravity and quantum mechanics. Beyond theoretical physics, the discovery of the first black hole could also have profound implications for our understanding of cosmic evolution. If black holes existed before the first galaxies, they might have played a fundamental role in shaping the early universe. Some theories suggest that early black holes helped reionize the universe, the process that made it transparent to light after the cosmic dark ages. The powerful radiation emitted by growing black holes could have contributed to heating and ionizing intergalactic gas, influencing the formation of the first galaxies. Additionally, if the first black holes were more numerous than expected, it could mean that the early universe was much more active and chaotic than previously thought. This would have consequences for our models of galaxy formation, possibly requiring a major revision of how cosmic structures emerged from the primordial soup of the Big Bang. A particularly exciting scenario is the possibility that the first black hole might still exist today. While many ancient black holes would have merged or grown into larger structures, some could have survived relatively unchanged. If we were to detect an ancient, isolated black hole that has remained untouched since the early universe, it would be like finding a fossil from the dawn of time. Studying such an object could provide an unprecedented glimpse into the physics of the early cosmos. There is also a chance that the first black hole may not be what we expect at all. Some speculative theories propose that black holes might not be true singularities but instead exotic objects like gravastars or fuzzballs, hypothetical structures that mimic black holes but have no event horizon or singularity. If the first black hole turns out to be something entirely different, it could revolutionize our understanding of the fundamental nature of space and time. Furthermore, the discovery of the first black hole could inform the search for new physics in unexpected ways. If it turns out to be connected to dark matter, it could provide crucial evidence for one of the biggest unsolved mysteries in cosmology. Some models suggest that dark matter could be made of primordial black holes, and finding a first-generation black hole with unusual properties might confirm this theory. As our observational tools improve, the next decade could bring groundbreaking discoveries in this field. The upcoming 30-meter telescope, TMT, an extremely large telescope, ELT, will allow astronomers to peer deeper into the universe than ever before. Meanwhile, gravitational wave observatories like LISA will provide new ways to detect ancient black hole mergers, and X-ray telescopes like Athena will search for the high-energy signatures of the earliest accreting black holes. Ultimately, the search for the first black hole is about more than just finding an ancient object. It's about uncovering the fundamental processes that shaped our universe. Whether through direct imaging, gravitational waves, or exotic new physics, the discovery of the first black hole will be one of the most profound achievements in human history. It will reveal not only the origins of black holes but also the story of how the cosmos itself came to be. And as we stand on the brink of this discovery, we are reminded that the universe still holds mysteries far beyond our comprehension. The search for the first black hole is just one step in a much larger journey, one that continues to push the boundaries of knowledge and expand our understanding of the infinite depths of space and time. The implications of finding the first black hole ever formed extend far beyond astrophysics. It could reshape our understanding of time itself, revealing new insights into the fundamental laws governing the universe. If such a relic from the early cosmos is discovered, it might challenge not only our theories of black hole formation but also our entire framework of cosmology. Could this ancient black hole be a missing link between the primordial universe and the cosmic structures we observe today? Could it offer evidence for exotic processes that have remained hidden for billions of years? One of the most fascinating possibilities is that the first black hole could help us uncover the nature of dark matter. While black holes and dark matter are distinct phenomena, some theoretical models propose a connection. If the first black holes were numerous enough, they could account for a portion of the missing mass in the universe. This idea, known as the primordial black hole dark matter hypothesis, suggests that some fraction of dark matter might be made of ancient black holes formed in the first instance after the Big Bang. Unlike conventional dark matter candidates, such as weakly interacting massive particles, WIMPs, primordial black holes would be composed of ordinary matter but behave in ways that make them incredibly difficult to detect. If the first black hole is found and exhibits unusual properties, it could provide indirect evidence supporting this theory. Another groundbreaking consequence of detecting the first black hole would be the ability to study the physics of the early universe in unprecedented detail. Right now, our understanding of the universe's first moments is largely theoretical. The cosmic microwave background, CMB, provides a snapshot of the universe when it was just 380,000 years old. But before that, we rely on mathematical models. The discovery of the first black hole could offer a direct observational window into the epoch of cosmic inflation and the subsequent formation of the first structures. If it carries unique signatures, such as traces of exotic particles or unexpected gravitational interactions, it might reveal secrets about the conditions that existed mere seconds after the Big Bang. Additionally, the search for the first black hole is deeply connected to one of the most profound questions in physics: what happens at the singularity? General relativity predicts that the center of a black hole is a point of infinite density, where space and time cease to function as we know them. However, many physicists believe this is a sign that our current theories are incomplete. If the first black hole can be studied in detail, it might offer clues about the true nature of singularities. Could they be portals to other dimensions, as some speculative theories suggest? Could they be replaced by something else entirely, such as a Planck scale remnant or a quantum fuzzball? The first black hole might provide an observational test for these ideas, bridging the gap between general relativity and quantum mechanics. Beyond these theoretical implications, the first black hole could also tell us something deeply practical about how black holes interact with their surroundings. If it is found to be actively accreting material, it could provide new insights into the mechanisms of jet formation, accretion disks, and feedback processes, Studying such a system would allow astronomers to test models of how black holes consume matter and influence their environments. This is particularly relevant for understanding high-energy astrophysical phenomena, such as quasars and gamma-ray bursts, which are powered by similar accretion processes. There is also the possibility that the first black hole might not be a single object but rather a population of early black holes that formed under similar conditions. If multiple first-generation black holes are discovered, it would provide compelling evidence that black holes were common in the early universe. This would raise new questions. Why were they so abundant? Did they form in isolated pockets of extreme density, or were they the natural outcome of large-scale structure formation? If these ancient black holes are found in clusters, it could suggest that black hole mergers played a more significant role in shaping the early cosmos than previously thought. One of the biggest challenges in finding the first black hole is that it is likely to be incredibly faint. Over billions of years, it may have drifted away from dense regions of the universe, making it difficult to detect using traditional telescopes. However, new observational techniques could change this. Upcoming space-based observatories, such as the James Webb Space Telescope's successors, will have the sensitivity to detect faint objects at extreme distances. Additionally, gravitational wave detectors like the Laser Interferometer Space Antenna, LISA, could identify the ripples in space-time left behind by ancient black hole mergers, offering an indirect way to locate these primordial objects. Another potential method for detecting the first black hole involves looking for its influence on its surroundings. Even if it is no longer actively accreting material, it may still be detectable through its gravitational effects. If it exists in a binary system with a visible star, its presence could be inferred from the star's motion. Similarly, if it has a strong gravitational lensing effect, bending and distorting light from background objects, it might be possible to identify it through precise astronomical measurements. The discovery of the first black hole would not only be a scientific triumph but also a philosophical revelation. It would be a tangible connection to the universe's earliest moments, a direct link to the forces that shaped everything we see today. It would confirm that black holes were present at the dawn of time, playing an essential role in the evolution of galaxies, stars, and ultimately, life itself. As we continue to refine our instruments and deepen our theoretical understanding, the search for the first black hole remains one of the most thrilling quests in modern astrophysics. It is a search driven by curiosity, by the desire to unravel the cosmic story that led to our existence. Whether it is discovered tomorrow or a century from now, one thing is certain: when we finally find the first black hole, it will be a moment of profound scientific and existential significance. And perhaps, the search itself is just as important as the discovery. The quest for the first black hole pushes the boundaries of human knowledge, challenges our assumptions about the universe, and inspires future generations to look up at the night sky with wonder. The mystery remains unsolved, for now. But one day, we will look back at this moment as the beginning of a new era in our understanding of the cosmos. The search for the first black hole is not just a matter of scientific curiosity. It is a profound journey into the origins of the cosmos itself. If we can find this ancient object, we may unlock secrets that redefine our understanding of space, time, and the fundamental forces that shape the universe. It is a question that bridges disciplines, uniting astronomers, physicists, and cosmologists in a shared pursuit of the most elusive relic from the dawn of existence. One of the most intriguing possibilities is that the first black hole might not conform to the black holes we observe today. Most black holes in the modern universe form from the collapse of massive stars, but the earliest black holes may have emerged through completely different mechanisms. Some theories suggest that these black holes could have formed directly from collapsing regions of extremely dense gas in the early universe. Unlike stellar mass black holes, which require the death of a star, these so-called direct collapse black holes could have formed in environments where gravity overwhelmed all opposing forces, creating black holes on a massive scale without any prior stellar evolution. If direct collapse black holes did exist in the early universe, they could explain how supermassive black holes, millions or even billions of times the mass of our Sun, formed so quickly. Today, we observe these colossal black holes at the centers of galaxies, but their rapid growth remains a mystery. The discovery of the first black hole could provide the missing link, showing that some black holes were born already massive, allowing them to grow into the behemoths we see today. But what if the first black hole was not a singular anomaly? Some models predict that the early universe was filled with dense pockets of matter that could have produced not just one, but many primordial black holes. If this is the case, it raises the possibility that black holes played a far greater role in shaping the cosmic landscape than we ever imagined. Some researchers even speculate that the earliest black holes could have merged to form the seeds of galaxies, acting as gravitational anchors that pulled matter together, forming the first stars and structures in the universe. If we could locate the first black hole, it would serve as a cosmic time capsule, preserving clues about the extreme conditions of the early universe. It might contain traces of exotic physics that no longer exist today, perhaps remnants of high-energy particles that were abundant in the moments after the Big Bang. These relics could challenge or confirm some of the most ambitious theories in physics, including the nature of dark energy, the role of quantum gravity, and the behavior of spacetime at extreme densities. One of the most tantalizing possibilities is that the first black hole could provide direct evidence for quantum gravity. While general relativity describes black holes on large scales, it breaks down at the singularity, where quantum effects become dominant. If the first black hole still carries signatures of these quantum effects, perhaps in the way it interacts with surrounding matter or distorts spacetime, it could be the key to unifying the laws of physics. Some theories propose that black holes might not contain singularities at all, but instead be fuzzballs, or quantum remnants that defy classical descriptions. The first black hole might be the perfect laboratory to test these ideas. Another mystery surrounding the first black hole is whether it could still be actively interacting with its environment. If it has spent billions of years consuming matter, it might still be generating powerful radiation, detectable through X-ray or radio observations. However, if it has drifted into a region of space where little matter remains, it could be nearly invisible, making it one of the hardest objects in the universe to detect. If we do find it, the nature of its surroundings could tell us about its journey through cosmic time, whether it has remained in a dense galaxy or traveled through the vast emptiness of intergalactic space. A critical tool in this search is gravitational wave astronomy. Since traditional telescopes rely on detecting electromagnetic radiation, light, X-rays, or radio waves, black holes pose a unique challenge because they do not emit light. However, black holes can be detected through their gravitational effects. When black holes merge, they release gravitational waves, ripples in spacetime that travel across the universe. If we can detect a gravitational wave signal from an ancient black hole, it might provide the first indirect evidence of its existence. The upcoming Laser Interferometer Space Antenna, LISA, a space-based gravitational wave detector, may be capable of detecting signals from black holes formed in the early universe, offering a new way to search for these elusive objects. But what if the first black hole is even stranger than we expect? Some speculative theories suggest that black holes could be gateways to other regions of spacetime. While this idea remains highly controversial, the nature of black hole interiors is still one of the biggest mysteries in physics. If the first black hole exhibits unusual behavior, such as deviations from expected gravitational effects, it might hint at new physics that challenge our current understanding of space and time. Could black holes connect different parts of the universe, or even different universes? The discovery of the first black hole might provide clues to one of the most profound questions in cosmology. Even if the first black hole does not reveal exotic new physics, its discovery would still revolutionize our understanding of cosmic evolution. It could confirm or rule out theories about how the first galaxies formed, how black holes influenced the cosmic web, and whether black holes contributed to reionization, the process that transformed the universe from an opaque state into the transparent cosmos we see today. Every detail of this ancient black hole, from its mass to its spin, could provide critical insights into the forces that shape the modern universe. As our observational capabilities continue to improve, the search for the first black hole remains one of the most exciting frontiers in astronomy. Future telescopes, such as the Extremely Large Telescope, ELT, and the Square Kilometre Array, SKA, will have unprecedented sensitivity, capable of detecting the faintest signals from the most distant objects. Meanwhile, advancements in artificial intelligence and machine learning are allowing astronomers to sift through massive datasets, identifying potential candidates that might have been overlooked by traditional methods. The journey to find the first black hole is not just a scientific endeavor, it is a testament to humanity's unrelenting curiosity. It is a quest to understand the origins of the universe, to glimpse the forces that shaped everything we see today, and to confront some of the deepest mysteries of existence. Whether this ancient black hole has been hiding in the depths of a distant galaxy or wandering through the cosmic void, its discovery will mark a turning point in our exploration of the cosmos. One day, perhaps sooner than we think, we may finally find the first black hole ever formed. And when we do, it will be more than just a discovery, it will be a revelation. A window into the past, a challenge to our current theories, and a new beginning in our quest to understand the universe. The search for the first black hole is an endeavor that not only stretches the boundaries of our technological capabilities but also challenges our very understanding of the universe's infancy. The discovery of such a primordial black hole would provide a rare glimpse into an era so distant that even the cosmic microwave background radiation, the faint afterglow of the Big Bang, barely reaches us from that time. This means that locating the universe's first black hole is akin to discovering a fossil from the dawn of time itself, an imprint left behind by the earliest cosmic processes that shaped everything we know today. One of the greatest mysteries surrounding the formation of the first black holes is whether they emerged independently or if they were part of a larger cosmic process that gave rise to galaxies. Current observations suggest that supermassive black holes existed in the early universe, but how they formed so quickly remains an open question. If black holes grew only through the gradual accumulation of matter, then the first black holes should have been much smaller, needing billions of years to grow into the giants we see today. However, if we find evidence that the first black hole was already massive at its birth, it would imply that the universe had mechanisms for forming large black holes almost instantly after the Big Bang. This brings us to the idea of seed black holes. In modern astrophysics, we often think of black holes as growing from the remnants of dying stars. However, in the earliest universe, there were no stars at all, only dense clouds of gas, radiation, and dark matter. Some models suggest that regions of extreme density could have collapsed directly into black holes, bypassing the need for stars entirely. These seed black holes would have been the foundation upon which galaxies formed, pulling in matter and shaping the first cosmic structures. If the first black hole ever formed was such a seed, then it might still be lurking somewhere, possibly at the center of an ancient galaxy that has remained relatively undisturbed for billions of years. Another possibility is that the first black holes were not singular but instead part of a larger population of primordial black holes that formed throughout the universe. Some theories suggest that tiny fluctuations in the density of the early universe could have led to the spontaneous formation of black holes in multiple locations. If this is the case, then the first black hole might not be alone. It could be one of many ancient black holes scattered across the cosmos. These primordial black holes are particularly interesting because they could help explain one of the biggest mysteries in physics: dark matter. If a significant portion of the universe's dark matter is made up of ancient black holes, then finding the first one might also solve the puzzle of what makes up most of the universe's mass. But how can we even detect such an ancient black hole? The problem with finding the first black hole ever formed is that, by its nature, it does not emit light. Unlike stars or galaxies, black holes do not shine on their own. They are detected only through their gravitational influence on nearby matter. This means that our best chance of finding the first black hole is by looking for indirect clues, signs that something massive but invisible is affecting its surroundings. One way astronomers are searching for the first black hole is by looking for quasars, extremely bright objects powered by black holes consuming large amounts of matter. Some quasars have been found at incredible distances, meaning they existed when the universe was only a few 100 million years old. If we can identify a quasar that is even older than the ones we have already found, it could be linked to one of the very first black holes. Another approach involves gravitational lensing, a phenomenon where the gravity of a massive object bends and magnifies light from more distant sources. If a black hole from the early universe passes in front of a distant star or galaxy, it could temporarily magnify its light, allowing us to detect it. While this method is challenging, new instruments like the Vera C. Rubin Observatory are expected to provide unprecedented insights into these cosmic events. Gravitational waves are another promising avenue. When black holes merge, they release ripples in spacetime that can be detected by observatories like LIGO and Virgo. If we were to detect a gravitational wave signal from a black hole merger that took place in the very early universe, it could provide direct evidence of the first black holes. Upcoming space-based gravitational wave detectors, such as LISA, may offer the sensitivity needed to detect these ancient events. However, what if the first black hole is not behaving the way we expect? Some researchers propose that black holes could slowly evaporate over time due to a process called Hawking radiation. If the first black hole was small enough, it might have already evaporated, leaving behind no trace of its existence. On the other hand, if it has continued to grow by consuming matter, it could now be far larger than we expect, possibly hiding in a distant galaxy, or even drifting through intergalactic space. Another speculative idea is that the first black hole could have undergone unusual interactions with dark matter. If dark matter is made up of exotic particles that interact weakly with normal matter but strongly with black holes, then the first black hole might still carry signatures of these interactions. Detecting such a signal would revolutionize our understanding of both black holes and dark matter. But what if the first black hole is something even stranger? Some theories suggest that in the early universe, before traditional black holes could form, there could have been objects known as gravastars or black stars, hypothetical entities that mimic black holes but contain exotic states of matter that prevent true singularities from forming. If the first black hole we discover turns out to be one of these exotic objects, it would challenge everything we thought we knew about black holes and force us to reconsider fundamental physics. As we continue the search, one thing is certain: the discovery of the first black hole ever formed would be one of the most groundbreaking findings in history. It would provide insight into the conditions of the early universe, reveal whether black holes played a key role in cosmic evolution, and potentially unlock new laws of physics. Whether we find it tomorrow or a century from now, its discovery will mark a new era in our quest to understand the cosmos. Even if the first black hole itself remains elusive, the search for it is already pushing the boundaries of human knowledge. Each new observation, each new theory, and each new technological breakthrough brings us closer to answering the ultimate question: what was the first black hole like, and how did it shape the universe we see today? Perhaps somewhere out there, in the depths of space and time, the first black hole still lingers, waiting to be found. And when we finally discover it, we will not only have uncovered one of the universe's oldest secrets, but also taken one step closer to understanding the nature of reality itself. The search for the first black hole ever formed is not just a quest to find a single object. It is an attempt to peer into the universe's infancy and understand the very foundation upon which all cosmic structures were built. The implications of this search stretch far beyond astronomy, touching on fundamental physics, the nature of dark matter, and the evolution of galaxies. If we succeed in uncovering the first black hole, we will be answering one of the deepest mysteries about how the universe transitioned from chaos to order. One of the most perplexing questions that astronomers and physicists are grappling with is how such an early black hole could have formed at all. The prevailing models of black hole formation suggest that they typically arise from the remnants of massive stars that have exhausted their nuclear fuel and collapsed under their own gravity. However, in the early universe, before the first stars had even formed, there should not have been any stellar remnants to create black holes in the traditional way. This paradox raises the possibility that the first black hole formed through entirely different mechanisms. One leading theory proposes that the first black hole may have emerged from the direct collapse of extremely dense gas clouds in the primordial universe. In this scenario, vast reservoirs of hydrogen and helium, the only elements present in significant quantities during the universe's first few 100 million years, could have accumulated in a single region of space, reaching such an immense density that the gas itself collapsed into a black hole without ever forming a star. If this process did occur, then the first black hole could have been significantly larger than typical stellar mass black holes, possibly reaching tens of thousands, or even millions of solar masses right from the beginning. Another intriguing idea is that the first black hole might not have formed naturally at all, but rather as a byproduct of the extreme physics present during the first moments after the Big Bang. Some theories suggest that high-energy quantum fluctuations in the early universe could have produced microscopic black holes, which then grew over time as they absorbed matter. These so-called primordial black holes would be unlike any black holes we see today, having formed not from the death of a star but from the very fabric of spacetime itself. If such a black hole were discovered, it would provide direct evidence for these early universe conditions and possibly offer insights into physics beyond the standard model. The role of dark matter in this story cannot be ignored. While normal matter, the kind that makes up stars, planets, and even our own bodies, interacts through electromagnetism, allowing us to see and touch it, dark matter remains invisible and undetectable except through its gravitational influence. Some theories suggest that dark matter could have played a crucial role in the formation of the first black hole by providing the necessary mass to trigger its collapse. If true, this would link the search for the first black hole to one of the biggest mysteries in cosmology. What is dark matter? Could dark matter itself have seeded the birth of the first black holes, acting as the hidden scaffolding upon which the early universe took shape? Despite the theoretical possibilities, detecting the first black hole remains an incredible challenge. Since black holes do not emit light, astronomers must rely on indirect methods to find them. One approach involves searching for signs of gravitational lensing, where the immense gravity of an unseen object bends and magnifies the light from more distant celestial bodies. If a primordial black hole is drifting through space, it could occasionally pass in front of a distant star, briefly magnifying its brightness in a way that could be detected by telescopes. Another promising method is looking for the remnants of ancient quasars, extremely luminous objects powered by supermassive black holes consuming vast amounts of matter. If we can identify a quasar that dates back to the earliest epoch of the universe, it might be linked to one of the first black holes ever formed. Advanced telescopes, such as the James Webb Space Telescope, are now capable of peering deeper into the cosmos than ever before, potentially revealing quasars that existed when the universe was only a few 100 million years old. Gravitational wave astronomy also offers a unique opportunity to detect ancient black holes. When black holes merge, they send ripples through the fabric of spacetime, gravitational waves, that can be detected by observatories like LIGO and Virgo. If a gravitational wave signal is detected from a black hole merger that took place in the very early universe, it could provide direct evidence of the first black holes. Future space-based observatories, such as the Laser Interferometer Space Antenna, LISA, will be even more sensitive to these signals, potentially unlocking the ability to detect black hole mergers from the earliest periods of cosmic history. As we push the limits of our observational technology, we must also consider more speculative possibilities. What if the first black hole does not behave like the ones we observe today? Some physicists propose that instead of traditional black holes, the early universe may have contained exotic objects known as gravastars or dark stars, hypothetical entities that mimic black holes but contain different forms of matter or energy inside them. If such an object were discovered, it would challenge our understanding of gravity and quantum mechanics, forcing us to reconsider fundamental principles of physics. Even if the first black hole has since merged with others or grown beyond recognition, its discovery would be one of the most groundbreaking achievements in modern astrophysics. It would allow us to reconstruct the timeline of the universe's earliest moments, providing insight into how structure formed and evolved. It would tell us whether black holes played a role in shaping galaxies, whether dark matter influenced their birth, and whether entirely new physics was at play in the early cosmos. The search continues, with astronomers scanning the skies, physicists refining their models, and engineers developing ever more advanced instruments to probe the depths of space. The first black hole ever formed may be hidden among the billions of galaxies we see today, or it may exist in a state we have yet to understand. But one thing is certain: when we finally uncover it, we will not just be finding a black hole, we will be revealing a piece of the universe's origin story, a missing link in our cosmic history. Perhaps, at this very moment, the first black hole still lingers in the darkness of deep space, waiting for its story to be told. And when we finally detect it, it will not only redefine our knowledge of the cosmos but also bring us closer to answering the ultimate question: how did everything begin? The implications of discovering the first black hole ever formed extend beyond astronomy and into the very fabric of physics itself. If we find it, we will not only gain insight into how the first structures in the universe formed but also challenge and refine some of our most fundamental theories about space-time, quantum mechanics, and even the nature of reality. One of the greatest mysteries surrounding black holes is their interaction with quantum mechanics. According to general relativity, black holes are regions where gravity is so intense that nothing, not even light, can escape. However, quantum mechanics, the theory governing the behavior of particles on the smallest scales, suggests that black holes should not be completely isolated from the rest of the universe. Stephen Hawking's groundbreaking work introduced the idea of Hawking radiation, a process in which black holes slowly evaporate over time. If the first black hole ever formed still exists today, it may hold crucial clues about whether Hawking radiation actually occurs, and whether black holes ultimately disappear or leave behind some form of exotic remnant. Another profound question concerns the information paradox. When matter falls into a black hole, its information, such as the details of the particles that made it up, seems to be lost forever. But according to quantum mechanics, information can never truly be destroyed. This apparent contradiction between quantum mechanics and general relativity has puzzled physicists for decades. If the first black hole ever formed has survived and can be studied, it could provide critical evidence that helps resolve this paradox. Some theories suggest that information might be preserved on the event horizon in a holographic form, while others propose that black holes might eventually release all their information back into the universe. Beyond physics, the search for the first black hole also has profound implications for understanding the evolution of galaxies. The supermassive black holes found at the centers of galaxies today must have started out as much smaller objects in the early universe. If we can identify the first black hole, we may be able to trace the growth of these cosmic giants and determine whether they formed through the gradual accumulation of matter or through rapid mergers with other black holes. This, in turn, would help us understand why galaxies take the shapes they do, and why some galaxies host extremely active quasars while others appear relatively quiet. There is also the possibility that the first black hole was unlike anything we currently imagine. Some theories suggest that instead of forming from collapsing stars, the first black holes could have emerged as part of the cosmic inflation process, the brief period of exponential expansion that occurred right after the Big Bang. If true, these black holes might not behave like the ones we see today. They could be linked to dark matter, or they might be gateways to other dimensions if certain interpretations of string theory hold true. The observational challenge of finding the first black hole is enormous. Since black holes do not emit light, we must rely on indirect evidence to locate them. But if the first black hole was truly primordial, it may have left subtle imprints on the cosmic microwave background radiation, the faint glow of heat left over from the Big Bang. Advanced telescopes like the Planck satellite and future missions may be able to detect these imprints, revealing clues about the first black holes and the role they played in shaping the universe. Another avenue of research involves searching for ancient gravitational wave signals. When black holes merge, they send ripples through spacetime that can be detected by observatories like LIGO and Virgo. If we can find gravitational wave signals originating from a time when the universe was only a few 100 million years old, they might point us toward the very first black holes. Upcoming space-based gravitational wave detectors, such as the Laser Interferometer Space Antenna, LISA, will be able to detect these ancient signals with unprecedented precision. The search for the first black hole is not just about solving a cosmic puzzle, it is about understanding our own origins. Every galaxy, every star, every planet, and every atom in our bodies ultimately traces its history back to the conditions that existed in the early universe. If the first black hole played a role in shaping the cosmos, then in a very real sense, it also played a role in creating the world we see today. And so the search continues. Every new telescope, every new experiment, and every new theory brings us one step closer to uncovering the truth. Perhaps the first black hole is still out there, drifting in the vast emptiness of space, waiting to be discovered. Or perhaps it has long since merged with others, becoming part of the cosmic web that binds the universe together. Either way, when we finally find it, we will not only be looking into the depths of space, we will be looking back in time, to the very moment when everything we know began. The search for the first black hole ever formed is more than an astronomical quest. It is a journey to the very beginning of time, a search for the oldest and most enigmatic object in the universe. As we continue to develop new technologies and refine our theories, we are getting closer to answering one of the biggest questions in cosmology. How did the first black hole come into existence? And what role did it play in shaping everything that followed? One of the most significant challenges in this search is the extreme distance involved. The first black hole would have formed more than 13 billion years ago, meaning that any light or radiation associated with it would be traveling across nearly the entire observable universe before reaching us. This makes direct observation incredibly difficult, requiring telescopes that can peer deeper into space than ever before. The James Webb Space Telescope, JWST, which was designed specifically to study the early universe, is one of our best tools for this mission. By analyzing distant quasars and the faint light of ancient galaxies, JWST may provide crucial clues about the earliest black holes. But even with powerful telescopes, how do we actually detect a black hole that formed so long ago? Black holes themselves do not emit light, making them invisible to traditional observations. Instead, astronomers must look for indirect signs of their presence. One approach is to study the light from ancient quasars, supermassive black holes at the centers of galaxies that are actively consuming matter. If we can find a quasar that dates back to the first few 100 million years of the universe, it could be linked to one of the earliest black holes ever formed. Another method involves looking for the gravitational effects of ancient black holes. According to Einstein's theory of general relativity, massive objects like black holes warp the fabric of spacetime around them. If a black hole passes in front of a distant star or galaxy, it can bend and magnify the light from that background object in a process known as gravitational lensing. By studying these distortions, astronomers may be able to identify black holes that existed in the early universe. There is also the possibility that the first black holes formed in a way completely different from modern black holes. Some theories suggest that they could be primordial black holes, objects that formed not from collapsing stars, but from the extreme density fluctuations in the first moments after the Big Bang. If primordial black holes exist, they could explain some of the biggest mysteries in physics, including the nature of dark matter. Some researchers believe that dark matter could actually be made up of a vast population of these ancient black holes, scattered throughout the universe but remaining undetectable except through their gravitational effects. If we could confirm the existence of primordial black holes, it would revolutionize our understanding of both cosmology and particle physics. It would provide evidence that black holes can form through mechanisms other than stellar collapse, and it would offer a new perspective on the role of black holes in the evolution of the universe. Some scientists have even speculated that tiny primordial black holes could still be evaporating today through Hawking radiation, potentially producing detectable signals that could be observed with future space telescopes. Gravitational wave astronomy also offers a new way to detect the first black holes. When two black holes merge, they produce powerful ripples in space-time known as gravitational waves. These waves travel across the universe, carrying information about the black holes that created them. The Laser Interferometer Gravitational Wave Observatory, LIGO, and its European counterpart, Virgo, have already detected dozens of black hole mergers. But so far, all of these detected events have involved black holes that formed much later in cosmic history. If we could detect a gravitational wave signal from a black hole merger that occurred when the universe was less than 1 billion years old, it would provide direct evidence of the first generation of black holes. Future missions like the Laser Interferometer Space Antenna, LISA, a space-based gravitational wave detector, will be capable of detecting much lower frequency waves than LIGO. This means LISA could potentially detect the mergers of supermassive black holes in the early universe, providing new insights into how the first black holes grew and evolved. If we find that these ancient black holes were merging frequently, it would suggest that black holes played a much more significant role in shaping the early universe than previously thought. But what if the first black hole still exists today? Could it have survived unchanged for more than 13 billion years, drifting through space as a silent relic of the past? If so, it would be one of the oldest structures in the universe, predating even the formation of galaxies. Finding such a black hole would be an incredible discovery, allowing us to study an object that has remained virtually untouched since the dawn of time. However, there is also the possibility that the first black hole has long since merged with others, becoming part of a much larger black hole at the center of a galaxy. If this is the case, then the first black hole may no longer be distinguishable from the countless other black holes in the universe. But even if we cannot find the original black hole itself, we may still be able to detect its effects on the early universe. By studying the oldest galaxies, the oldest stars, and the oldest quasars, we can look for signs that the first black holes played a role in their formation. The search for the first black hole is, in many ways, a search for our own origins. The conditions that allowed black holes to form in the early universe are the same conditions that eventually gave rise to galaxies, stars, and planets. If black holes helped shape the structure of the cosmos, then in a very real sense, they also shaped the world we live in today. Perhaps the first black hole still lingers in the depths of space, hidden from view but exerting its gravitational influence on the universe around it. Or perhaps it has become part of something greater, its legacy imprinted on the galaxies and stars that emerged in its wake. Either way, when we finally uncover the truth about the first black hole, we will be answering one of the most fundamental questions about the nature of existence. How did everything we see today come to be? As astronomers continue their search, using ever more advanced instruments and techniques, the discovery of the first black hole may be closer than we think. And when we do find it, it will not just be a moment of scientific triumph, it will be a glimpse into the very first moments of our universe, a window into the past that could reshape everything we know about the cosmos. The search for the first black hole ever formed is a pursuit that stretches the limits of human ingenuity, scientific knowledge, and technological capability. It is a journey that not only takes us to the furthest edges of the observable universe but also forces us to confront some of the most perplexing questions about physics, space-time, and the origins of structure in the cosmos. Every new discovery in this field brings us closer to answering one of the most fundamental mysteries. What was the role of black holes in the infancy of the universe? One of the most intriguing aspects of this search is the relationship between the first black holes and the first galaxies. Modern galaxies are often home to supermassive black holes at their centers, some containing millions or even billions of times the mass of the Sun. However, in the earliest stages of the universe, these supermassive black holes must have started as much smaller objects, possibly the remnants of the very first stars. Understanding how these early black holes grew and merged over time can shed light on the formation of the cosmic structures we see today. Recent observations suggest that some quasars, extremely bright, active galactic nuclei powered by supermassive black holes, existed when the universe was less than 1 billion years old. This is astonishing because it implies that black holes in the early universe were able to grow to enormous sizes in an incredibly short amount of time. Standard models of black hole growth, which rely on the slow accumulation of matter, struggle to explain how these objects could have become so massive so quickly. This has led to several competing hypotheses. One possibility is that the first black holes grew through a process known as direct collapse. Instead of forming from the remnants of individual stars, these black holes may have formed directly from massive clouds of gas that collapsed under their own gravity. This would allow them to start with much larger initial masses and reach supermassive sizes much more rapidly. If this theory is correct, then the first black holes would have been fundamentally different from the stellar mass black holes we see forming in the present-day universe. Another theory suggests that early black holes merged at an exceptionally high rate. In the chaotic environment of the early universe, where galaxies were still forming and colliding frequently, black holes may have had many opportunities to merge and grow. This could help explain why we see quasars powered by supermassive black holes so early in cosmic history. Gravitational wave detectors like LISA may one day provide direct evidence of these ancient mergers, offering a glimpse into the violent and dynamic processes that shaped the first black holes. But what if some of the first black holes did not grow into supermassive giants? What if some remained relatively small and have been drifting through space, largely unnoticed, for more than 13 billion years? If such ancient black holes still exist, they may be detectable through their gravitational effects. These objects could be part of the mysterious dark matter that makes up most of the universe's mass. If primordial black holes make up even a small fraction of dark matter, they could be responsible for some of the strange gravitational anomalies observed in galaxies and galaxy clusters. The idea that black holes could be a component of dark matter is highly controversial but has gained renewed interest in recent years. Some scientists have proposed that if primordial black holes formed in the early universe, they could account for at least part of the missing mass that gravitational studies suggest must be present. Future observational missions, including the Vera C. Rubin Observatory and upcoming space-based telescopes, may be able to detect microlensing events, brief periods where a black hole passes in front of a distant star and magnifies its light, offering a new way to identify these elusive objects. The search for the first black hole is also a test of our understanding of fundamental physics. Black holes are some of the most extreme environments in the universe, where gravity is so strong that it warps space and time itself. By studying black holes, we can explore the limits of general relativity and quantum mechanics, two of the most successful but seemingly incompatible theories in modern physics. One of the most pressing questions in theoretical physics is whether black holes obey the laws of quantum mechanics, or if they require a new, as yet undiscovered framework to fully describe them. If we could find and study the first black hole ever formed, it might provide evidence for quantum gravitational effects that could lead to the long-sought unification of quantum mechanics and general relativity. Some physicists believe that black holes may be key to understanding the true nature of space-time itself, potentially revealing insights into hidden dimensions, quantum information theory, and even the structure of the multiverse. The existence of the first black hole is more than just a historical curiosity. It represents the earliest phase of structure formation in the universe. Before the first stars ignited, before galaxies formed, and before planets existed, black holes may have been among the first stable structures to emerge from the chaos of the Big Bang. Their influence on the evolution of the universe may be far greater than we currently understand. Every major telescope and space mission planned for the coming decades, whether it is searching for exoplanets, mapping cosmic radiation, or detecting gravitational waves, may contribute to solving the mystery of the first black hole. New discoveries in this area will not only reshape our understanding of black holes but also deepen our knowledge of how the universe evolved from a featureless sea of energy into the vast and complex cosmos we see today. If and when we finally detect the first black hole, it will be one of the most profound discoveries in the history of science. It will allow us to look back further in time than ever before, to witness the birth of the very first cosmic structures, and to unlock the secrets of how the universe took shape. The search for this ancient relic continues, and with every passing year, we come closer to finding the answer hidden in the depths of space. Perhaps one day, a signal from the first black hole will reach us, a whisper from the dawn of time, carrying with it the echoes of creation. As astronomers push the limits of their technology in the search for the first black hole, they are also confronted with fundamental questions about how black holes influence the very fabric of the universe. The role of black holes in cosmic evolution remains one of the greatest unsolved mysteries in astrophysics. If the first black holes formed early enough, they may have played a key role in shaping the structure of the universe as we know it. Their gravitational pull could have influenced the formation of galaxies, altered the movement of cosmic gas, and even affected the spread of dark matter. One of the most intriguing aspects of early black holes is how they may have helped ignite the first stars. In the early universe, before the first stars formed, the cosmos was a vast expanse of mostly hydrogen and helium gas. These elements clumped together under gravity, forming the first stars, known as population 3 stars. These stars were massive, burning hotter and living much shorter lives than the stars we see today. When they exploded in supernovae, they seeded the universe with heavier elements, setting the stage for future generations of stars and planets. But could black holes have formed even before the first stars? Some theories suggest that primordial black holes, which may have formed just moments after the Big Bang, could have been among the first objects in the universe. If these black holes existed, they might have served as seeds that helped accelerate the formation of galaxies by pulling in gas and triggering the collapse of surrounding matter. Alternatively, they could have remained hidden, drifting through space undetected, influencing the structure of the cosmos in ways we have yet to understand. The search for the first black hole is also deeply connected to the study of quasars, some of the brightest and most powerful objects in the universe. Quasars are powered by supermassive black holes that consume surrounding matter, producing vast amounts of energy. Some of the most distant quasars ever observed existed less than 1 billion years after the Big Bang, meaning their central black holes must have grown to enormous sizes in a very short time. This challenges our current understanding of black hole growth, as the process of accretion, where black holes pull in matter, should take much longer to reach such immense masses. One explanation for the rapid growth of early black holes is the idea of super-Eddington accretion, where black holes consume matter at rates far beyond what is typically expected. In most cases, there is a limit to how fast a black hole can grow because the radiation pressure from infalling material pushes away additional matter. However, under certain conditions, this limit might be exceeded, allowing early black holes to grow at an accelerated pace. Observations of distant quasars suggest that some early black holes may indeed have grown much faster than standard models predict, possibly explaining how they reached their supermassive sizes so quickly. Another possibility is that the first black holes formed from the direct collapse of massive gas clouds. Unlike the black holes we observe today, which typically form from the remnants of exploded stars, these early black holes may have emerged directly from enormous clouds of primordial gas. This process would allow them to start with masses thousands of times greater than typical stellar mass black holes, giving them a significant head start in their growth. If this theory is correct, then the first black holes were unlike anything we have observed in the present-day universe. Detecting these ancient black holes is an extraordinary challenge. The universe has expanded tremendously since the time when these objects first formed, and the light emitted by early black holes has been stretched by cosmic expansion, shifting into infrared wavelengths. This makes them difficult to observe using traditional telescopes, which are primarily designed to detect visible light. However, next-generation observatories like the James Webb Space Telescope, JWST, and upcoming missions such as the Nancy Grace Roman Space Telescope are specifically designed to peer into the infrared spectrum, potentially revealing some of the first black holes ever formed. Gravitational waves offer another promising way to detect early black holes. When black holes merge, they send ripples through spacetime, which can be detected by instruments like LIGO and Virgo. Future space-based detectors, such as the Laser Interferometer Space Antenna, LISA, will be capable of detecting gravitational waves from much earlier periods in cosmic history. If we can observe mergers between ancient black holes, it would provide direct evidence of their existence, and help us understand how they evolved over time. Some researchers believe that the first black holes might still be hiding in plain sight. If primordial black holes make up even a small fraction of dark matter, they could be responsible for certain unexplained gravitational effects observed in galaxies. Microlensing studies, where a black hole passes in front of a distant star and magnifies its light, could provide clues about the existence of these elusive objects. Upcoming surveys, such as those conducted by the Vera C. Rubin Observatory, may help determine whether small, ancient black holes still roam the universe today. The search for the first black hole is not just about uncovering the past, it is also about understanding the future. Black holes are among the most mysterious objects in the universe, and their study may unlock the secrets of quantum gravity, dark matter, and the nature of spacetime itself. Some physicists believe that black holes could hold the key to a theory of everything, unifying our understanding of gravity with the principles of quantum mechanics. If we can discover and study the first black hole, it may provide a glimpse into physics beyond our current understanding, opening the door to new realms of scientific exploration. As technology continues to advance, the search for the first black hole will become even more precise. Future telescopes, gravitational wave detectors, and space missions will push the boundaries of what we can observe, allowing us to probe deeper into the origins of the universe. Whether through direct imaging, gravitational wave detection, or indirect evidence from cosmic structures, the discovery of the first black hole will be one of the most significant achievements in modern science. Perhaps one day, we will look back at this moment in history as the beginning of a new era in astrophysics, an era where we finally unlock the mysteries of black holes and their role in shaping the universe. Until then, the search continues, driven by the endless curiosity of scientists determined to uncover the truth about these enigmatic cosmic giants. The search for the first black hole ever formed is not just a quest to understand the past. It is also a journey into the most fundamental questions about the nature of reality itself. Black holes challenge our understanding of physics in profound ways, serving as the ultimate testbeds for theories that attempt to reconcile gravity with quantum mechanics. If we can find the first black holes, those that existed in the infancy of the universe, we may gain critical insights into how space, time, and matter evolved from the moment of the Big Bang to the structures we observe today. One of the most intriguing possibilities in this search is the idea that the first black holes could have formed before the first stars, existing as primordial black holes. If true, these objects would represent the oldest known structures in the universe, predating even the formation of galaxies. Theoretical models suggest that small quantum fluctuations in the density of the early universe could have led to regions of extreme compression, collapsing into black holes almost instantly. Unlike stellar mass black holes, which form from the remnants of dying stars, these primordial black holes could have emerged mere fractions of a second after the Big Bang. If primordial black holes exist, they could provide clues about some of the biggest mysteries in cosmology, including the nature of dark matter. Some researchers have proposed that a portion of dark matter might actually be made up of small, ancient black holes that formed in the first moments of cosmic history. These black holes would be incredibly difficult to detect directly, as they would not emit any light, but their gravitational influence on nearby stars and galaxies could reveal their presence. Microlensing studies, where the gravitational field of a black hole bends and magnifies the light from background objects, could offer the first evidence of these elusive objects. The discovery of the first black hole would also provide new insights into the role of black holes in cosmic evolution. Today, we know that supermassive black holes reside at the centers of most galaxies, including our own Milky Way. However, we still do not fully understand how these enormous black holes formed or how they grew so large in such a short period of time. If the first black holes were indeed primordial, they may have served as the seeds from which galaxies formed, drawing in gas and dust to create the vast cosmic structures we see today. Alternatively, if the first black holes formed from collapsing stars, they would provide a critical missing link in our understanding of the earliest stars and their life cycles. The first generation of stars, known as population 3 stars, were vastly different from the stars we observe today. Composed almost entirely of hydrogen and helium, these stars burned hotter and lived shorter lives, ending in either supernova explosions or direct collapses into black holes. If we can find evidence of these first stellar black holes, we will gain a better understanding of the conditions that shaped the early universe. One of the biggest challenges in detecting the first black holes is the vast distance between us and the time period in which they formed. The light from these early objects has been traveling for over 13 billion years, stretched by the expansion of the universe into infrared wavelengths. This is where telescopes like the James Webb Space Telescope, JWST, become crucial. Unlike previous observatories, JWST is specifically designed to detect faint infrared signals from the early universe, making it one of the most powerful tools in the search for ancient black holes. Another exciting avenue for detection comes from gravitational waves, ripples in space-time caused by massive cosmic events. When two black holes merge, they send out powerful gravitational waves that can be detected by instruments like LIGO and Virgo. While current gravitational wave detectors are limited to relatively recent black hole mergers, future missions like the Laser Interferometer Space Antenna, LISA, will be able to detect signals from much earlier in cosmic history. If ancient black holes merged in the early universe, LISA could provide direct evidence of their existence. Despite these challenges, astronomers are already making progress in the search for ancient black holes. Observations of the most distant quasars, bright objects powered by supermassive black holes, suggest that some black holes grew to enormous sizes within the first few 100 million years after the Big Bang. This raises an important question: how did these black holes grow so quickly? If black holes require time to accumulate mass through accretion, then the existence of such massive black holes in the early universe suggests that some may have started out much larger than expected. This could lend support to the idea that the first black holes formed from direct collapses of massive gas clouds rather than from the remnants of stars. There is also the possibility that the first black holes were created through exotic processes that we have yet to fully understand. Some physicists have speculated that extreme conditions in the early universe could have given rise to black holes through mechanisms outside of conventional astrophysical models. For example, some theories suggest that microscopic black holes could have formed due to high-energy interactions between quantum fields, only to later merge and grow into larger, detectable objects. If this is the case, then the first black holes might be linked to entirely new physics beyond the Standard Model. The implications of discovering the first black hole extend far beyond astrophysics. Black holes challenge our understanding of spacetime, pushing the limits of general relativity and quantum mechanics. If we can observe how the first black holes formed and evolved, we may gain insights into the nature of singularities, the points at the centers of black holes where gravity becomes infinitely strong. Understanding singularities could lead to breakthroughs in quantum gravity, helping to unify Einstein's theory of relativity with the strange world of quantum mechanics. As we look to the future, the search for the first black hole will only intensify. Upcoming missions and next-generation observatories, such as the Extremely Large Telescope, ELT, and the Square Kilometer Array, SK, will provide unprecedented detail about the early universe. These instruments will allow astronomers to peer deeper into space than ever before, capturing the light from some of the first black holes to form. The quest to find the first black hole is ultimately a quest to understand our origins. Black holes are among the most enigmatic objects in the universe, capable of bending light, warping time, and consuming everything in their paths. Yet, despite their destructive nature, they may also have played a fundamental role in shaping the universe as we know it. If we can unlock their secrets, we may finally answer some of the deepest questions about how everything, from galaxies to planets to life itself, came to be. The search continues, and with every new discovery, we come one step closer to uncovering the truth about the first black hole ever formed. The search for the first black hole ever formed is more than a scientific quest. It is a journey into the very origins of the cosmos, a mystery that could redefine everything we know about the early universe. If we can identify the first black hole, we might not only understand the birth of black holes but also uncover hidden aspects of cosmic history that remain shrouded in darkness. Every piece of evidence we gather adds to an unfolding puzzle, revealing the structure of the universe as it existed billions of years ago. One of the biggest challenges in detecting the first black hole is that these objects, by their very nature, do not emit light. Instead, they can only be detected through their interactions with their surroundings, either by observing how they distort light from nearby objects or by detecting the gravitational waves they produce. This makes the search extraordinarily difficult, as even the most advanced telescopes struggle to find indirect evidence of these elusive giants. However, despite these challenges, astronomers have made remarkable progress in identifying black holes from different stages of cosmic history. One promising approach is studying the most ancient quasars, supermassive black holes that are actively consuming matter and emitting vast amounts of energy. Some of the most distant quasars ever observed exist just a few 100 million years after the Big Bang, which suggests that their black holes must have formed even earlier. But how did these black holes grow so massive in such a short time? This is one of the biggest mysteries in modern astrophysics. If the first black holes formed from the collapse of massive stars, then there might not have been enough time for them to reach the enormous sizes observed in early quasars. This has led some scientists to propose alternative explanations, such as the idea that the first black holes could have formed from direct collapses of massive gas clouds rather than from supernova remnants. Another possibility is that black holes grew much faster than expected, possibly through a process known as super-Eddington accretion. Normally, there is a limit to how fast a black hole can grow, known as the Eddington limit, which is determined by the balance between the inward pull of gravity and the outward pressure of radiation. However, if certain conditions in the early universe allowed black holes to bypass this limit, perhaps by rapidly consuming dense clouds of gas, then they could have grown much faster than previously thought. This raises another intriguing question: could the first black holes have played a role in shaping the first galaxies? If black holes formed early enough, they could have acted as seeds for galaxy formation, influencing the distribution of matter and helping to shape the cosmic structures we see today. Some simulations suggest that early black holes could have triggered star formation by compressing gas clouds, while others indicate that the energy released by accreting black holes might have suppressed star formation by heating up the surrounding gas. Understanding the exact role of black holes in galaxy formation is one of the key goals of modern astrophysics, and finding the first black holes could provide crucial insights into this process. There is also the possibility that the first black holes were not formed by traditional astrophysical means but instead were created by exotic processes in the very early universe. Some theories suggest that quantum fluctuations in the density of the early universe could have created regions of extreme compression, leading to the formation of primordial black holes. These black holes would be fundamentally different from the black holes that formed from collapsing stars, as they would have existed since the first moments after the Big Bang. If primordial black holes exist, they could provide a unique window into the physics of the early universe. Some theories even suggest that primordial black holes could account for a portion of dark matter, the mysterious substance that makes up most of the universe's mass but has never been directly detected. If black holes of a certain size formed in the early universe, they could still exist today as invisible remnants of cosmic history, influencing the motion of stars and galaxies through their gravitational pull. Detecting these ancient black holes requires innovative approaches. One potential method is gravitational microlensing, where a black hole's gravity bends and magnifies the light from a background object, temporarily making it appear brighter. By monitoring large numbers of stars and galaxies for such brightening events, astronomers may be able to detect the presence of unseen black holes. Another promising method is using radio telescopes to search for the faint signals of black holes interacting with surrounding gas, which could reveal their locations even if they are not actively accreting matter. One of the most exciting developments in the search for the first black holes is the emergence of gravitational wave astronomy. The discovery of gravitational waves, ripples in spacetime caused by the merging of massive objects, has opened a new window into the universe. Future gravitational wave observatories, such as the Laser Interferometer Space Antenna, LISA, will be able to detect signals from much earlier in cosmic history, potentially revealing mergers of ancient black holes. If we can detect the gravitational waves from the first black hole mergers, we could confirm their existence and learn about their properties in unprecedented detail. Looking forward, the next generation of telescopes and observatories will play a crucial role in solving this mystery. The Extremely Large Telescope, ELT, and the Square Kilometer Array, SKA, will provide unparalleled views of the early universe, allowing astronomers to probe deeper than ever before. These instruments will be capable of detecting the faintest light from the first black holes, offering new clues about their formation and evolution. The search for the first black hole is ultimately a search for the universe's own origins. By uncovering how black holes formed and grew in the early universe, we can better understand the processes that shaped the cosmos as we see it today. Black holes are not just objects of destruction, they are also engines of creation, influencing the formation of galaxies and the evolution of cosmic structures. If we can find the first black hole ever formed, we may finally unlock some of the deepest secrets of the universe, answering questions that have puzzled scientists for decades. As we continue this search, we are reminded of the vastness of the cosmos and the mysteries it still holds. Every new discovery brings us closer to understanding the fundamental nature of reality itself. The first black hole may still be hidden somewhere in the depths of space, waiting to be found. But with each new observation, we take one step closer to uncovering one of the greatest cosmic mysteries of all time. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.